In the grand theater of the cosmos, amidst a myriad of distant suns and ancient galaxies, the Fermi Paradox presents a haunting silence, where a cacophony of alien conversations should exist. Where is everyone? Or are we alone? Welcome to Science and Futurism with Isaac Arthur, for our long-requested update to the Fermi Paradox Solution and Compendium episodes done back when the show was brand new, most of a decade ago. I am your host, the aforementioned Isaac Arthur, writer and narrator for the show, and also president of the National Space Society. Longtime watchers of the show can tell you there's few topics we spend more time on than the Fermi Paradox, and as we go through our entries today, I'll often reference other episodes that have explored a topic in greater detail, as our goal today is to give a quick but proper summary of all major concepts involved in the Fermi Paradox, not just solutions, but critical concepts like what a filter is, or how faster-than-light travel or entropy-violating machinery would alter the equation. Many of these topics are well known, others more obscure or newer, or old but newly named, and with deeper exploration and a paper doing some mathematical modeling. Some we've never looked at on the show before, others again have their own episodes. As we found out from other Compendium episodes, YouTube has a limit of 100 entries, so some have been merged together when they are overlapping. Some are being left out because I don't consider them very insightful, and we looked at them before in the prior Compendium. And so long as you don't mind my speech impediment, much stronger in those older videos contain information this one does not. Today's episode is not simply an update or expansion, it's a shift of focus to spend more time on some topics we've skimmed over in those prior editions and vice versa. Some get much deeper dives or again have their own whole dedicated episodes. There are some solutions I don't think are too insightful, but are so well known or asked after so regularly that we include them in here anyway. We have a lot of topics to cover today, and I anticipate this being our longest episode ever, much as the original two versions long held that title of longest video themselves, so a drink and a snack is advised, and if you enjoy the content, please hit the like and subscribe buttons, and check out the episode description for links to our online forums to find other folks to chat with about these topics or ways to help support the show, such as by donating to Patreon. As we go through these, be aware that while we're loosely using an encyclopedia format, we are not one and not trying to be one. I feel that would be too constraining and boring, but we are using alphabetical entries, and as with the other recent compendiums, my wife will be reading out the title and references bookending each entry to help break up the monotony of listening to me talk for a few hours. And the encyclopedia format also means you don't need to watch from start to finish, though you are certainly welcome to, or to return and watch what segments you wish. For those listening instead of watching, I've been running a list of all those topics and their time indices on the video while talking, and you can also find that list in the episode description alphabetically. Again, feel free to skip around and come back another day to view more, but a couple topics are paramount and vital to understand the Fermi Paradox, so we'll cover those first, and we might as well begin with the Fermi Paradox itself. Now, the first thing to understand about the Fermi Paradox is that it arises from the assumption that the universe is huge and ancient compared to our planet, that it probably has tons of planets like Earth, only older, and that since our planet has life, so would many of them. But the Fermi Paradox isn't just about if there's life out there, it's about there being life we could currently see and detect. That's obviously a moving goalpost since we keep getting better at finding signals, signs, and portents of life, or intelligent life. And for our purposes today, when we say intelligent life, what we mostly mean is technological life, those able to leave a techno signature we could detect, like a radio signal or an immense Dyson swarm, not intelligent dolphins or even Iron Age alien civilizations. The Fermi Paradox is also just a name, given to it in the 1970s by Michael Hart, one of the more active early discussers of the topic in serious scientific context, and it's probably very badly named. First, nobody actually thinks it's a real paradox. merely noting that to many people it seems paradoxical that a universe so immense and ancient should not be up to its eyebrows in ancient civilizations by now, and that we would expect to be able to detect them. Naming it for Enrico Fermi, a great physicist who also helped invent the hydrogen bomb, is also a bit dubious. Fermi didn't think it was a paradox and only has one brief known mention of the topic, where he simply opines that he doesn't think civilizations tend to last long before blowing themselves up, and that interstellar colonization is probably not practical. And again, he helped invent nuclear weapons and died before we landed on the moon, so it's not really surprising that he had been a touch pessimistic about our survival odds and galactic expansion. I would say this was essentially the default opinion of the science community for some time too, with lots of notable exceptions though. Shortly after the moon landings, when we were pretty optimistic about further space exploration, and when NATO and the Warsaw Pact seemed to be increasingly less likely to bury civilization in atomic ashes, we saw a lot of revisiting of the problem, and in the context of interstellar travel being possible, and that technology wasn't necessarily a ticking time bomb. This opened the doors to speculation, and Hart, a biologist, conjectured that a key concept of biology and Darwinian evolution is that life is going to try to expand and grow and find new niches wherever it can, filling up every rock in the galaxy so that they be impossible for us to miss. Thus, any explanation would need to either show how they couldn't do that, or could but would choose not to do that. He also begins discussion with what we call Fact A, that we have no demonstrable proof of alien existence at this time, which obviously is disputed by many. There are a large number of Fermi Paradox solutions that seek to show that alien civilizations cannot or will not grow, and one large section of those is that they can and would, but that life, or at least intelligent technological life, is so rare or recent that the universe is pretty empty, but not for long. This is the default perspective of the show and myself, incidentally, though as I like to stress, it's not that I believe in this position or think the evidence is strongest for it, but rather that it is also a weak position, just the least bad explanation. I've been poking and prodding at them for years before the show, and since starting the show I've probably been sent more proposed solutions and arguments for or against than nearly anyone else alive, and the show's online forums hosted more serious debate on the topic than any other place I can think of. My conclusion after many years is that all the proposed solutions have their issues, and we'll raise those as we go, and a lot of them share an issue like non-exclusivity, the Dyson Dilemma, or the time elapse argument, none of which are solutions themselves, but still get an entry of their own today. The next big camp of the Fermi Paradox is generally those who feel there's no paradox because aliens are here, and evidence of them is strong. And we'll look at some of those arguments today, but by and large, our Fermi Paradox episodes operate from the assumption we do not have strong evidence of aliens currently. Again, what some call Fact A, and our Alien Civilization series explores those options more. In those, we examine if a given alien group was acting a given way, what that would tell us, and if it fits the evidence folks often present. I generally do not like to do episodes discussing the veracity of any given bit of evidence here on Earth, though. I do not personally find any of it compelling, but I know lots of intelligent and thoughtful people who do, many are good friends as well, and it's a good place to insert the reminder and request that this show is all about questions and discussion, but also about courtesy, so please keep that in mind for any comments left on the video, replies to others, or dialogue in our forums. By default, this show and its audience tilt to the skeptical, though hardly universally, and my big reminder is that one of the reasons I do is not because I think aliens wouldn't visit Earth, but rather because I couldn't believe they would be able to do so and not pop in, and so we will be covering many of the solutions for why we might just not be seeing them, even though they are here and leaving evidence. Our third major camp is those who do not believe we're able to see the evidence, and this includes options like we just don't recognize that a mountain here on Earth is actually intelligent, or that the last alien visit was 1 million years ago and buried, or they are invisible alien visitors from parallel dimensions, or that their signals are so encoded and compressed or fundamentally alien that it just looks like white noise or a natural phenomena to us. So 3 core camps. We do not see aliens because they are rare. We do not see them because they are hard to see or hear, and we do not see them because we are unwilling or unable to. Then we have a number of solutions that overlap categories or don't fit into any, and in the prior videos we broke them down by camps, but I feel alphabetical order is better for today, and with that said, let's get started.
Aestivation Hypothesis.
Aestivation Hypothesis is a newer theory from 2017, and part of the wider general category that aliens are mostly dormant or hibernating, but here for the purpose of surviving to an era where they can better use their resources. Normally it wouldn't seem to make sense for a civilization to hibernate for eons, while others arrive to claim territory, but the notion goes that computation may be easier in an older and colder universe, under the Landauer computational limit. That at half the temperature, it takes half the energy to flip a bit or have a thought. If you're a post-biological entity, you can use that same energy or fuel to run vastly more computation, or thought or lifespan. Similar to rim migration or Hermit-Shoplifter hypothesis, it has the issue of leaving a vast supply of available galactic resources untouched, whereas a hibernating civilization planning for a post-stellar civilization for greater efficiency would be expected to ransack the galaxy to put everything into storage depots of some sort. And it would seem hard to argue they would prefer to sleep through this era when they could just send robots out to do the harvesting. It does not work well under non-exclusivity, since there is no compelling reason why some civilizations, or factions of civilizations, might decide not to hibernate, or might hibernate but do resource gathering first or automatically. We explore this idea of more efficient energy use by post-biologicals in our 2016 episode Civilizations at the End of Time, Black Hole Farming, though it is a different concept there as a civilization is not hibernating to the black hole era to do its living, just continuing life into that era.
See also Black Hole Farming, Hermit-Shoplifter Hypothesis, Non-Exclusivity, Resource Hoarding, Rim Migration. Aliens common but unrecognizable.
While it is common to ask if we can detect an alien signal or would notice a UFO trying to be discreet, there is also the argument that we, or aliens, or both, might just have a difficulty even recognizing that the other existed and was intelligent. A sentient glacier, thinking at a glacial pace, might not even realize that people walking over it existed, or vice versa, that the town they built in the shadow of that glacier was but a brief candle next to it. But our working theory on the show is that intelligence recognizes intelligence, especially in quantity. You might mistake a flint arrowhead for a common natural stone, or a flint axe head or knife, but not an entire tool shed complete with lots of squares and rectangles and wiring and metalwork, even if all those tools were made for alien hands, or tentacles. This notion that intelligence recognizes intelligence may not be universal, let alone applicable to life that might be visiting from some alternate reality or dimension, but it is critical to our approach to investigating cosmological phenomena that might be indicative of aliens. We might not be able to tell if some star dimming was a sign of a dust cloud, or a Dyson swarm, or a megastructure being built, but if it were artificial, we would expect other techno-signatures, like a lot of radio traffic or peaks in some other unlikely part of the EM spectrum, or similar disruption in neighboring systems that appeared to originate first at some central location. A city like New York shows its artificial nature in 10,000 unrelated ways, and by default we should expect an alien civilization to do the same. Nonetheless, we always need to be mindful that this is the ballpark notion that something artificial will often be accompanied by more artificial things and have multiple ways it appears artificial. And some we would expect might be absent. They may not use radio waves for communication. So too, one single aspect of that artificiality might be incredibly easy to spot, like a lighthouse beacon light being recognizable far further away than the many tools or structures nearby.
See also Techno and Bio-Signatures. Aliens used to visit Earth.
A common trope in sci-fi, as well as appearing in some religions, is that aliens used to visit Earth more in the past. This is a subset of ancient aliens, and one that usually assumes that humans were uplifted by those alien visitors, made either more intelligent or taught various ethics or engineering. This can range from benevolent to them visiting us to use us as slaves, as we see in the Stargate franchise. This tends to suffer from the problem of asking why the evidence of their visit isn't more obvious, and the question of where they went. And the former is more specific to this case, as while we can't point at feats of engineering like Stonehenge or the pyramids, we know how people of that era could have built them. It is a common misconception that we do not, when what we actually do not know is the specifics of how they were built, which is not the same thing, as we know a variety of methods they could have used that would have worked, and have a little evidence for some over others. Putting someone digging a ditch, for instance, does not imply alien help just because we do not know if they use a shovel, hoe, stick, flat rock as a scoop, or their bare hands. It also doesn't explain why there isn't more advanced tech out there, as while we often have folks say the more advanced technology is, the less durable it is, that is not inherently true. Any given device is exactly as durable as it is. Your technological level is at best loosely correlated. A modern slab of reinforced concrete is pretty durable. An ancient Egyptian pot or chair is not more durable than one built today, and with the intent of durability as opposed to price or weight. So there's no reason the only tech left over would be stone slabs unless they used incredibly fragile technology intentionally. Which they might have if the intent was to withdraw at some point, and they principally used nanotech for equipment maintenance, or they did an amazing job cleaning up. Which again they might have done if visiting to uplift a primitive species and leave them to carry on afterwards. But then you'd think they would have cleaned up better and removed all the proof folks tend to point to, like the giant pyramid or henge. Either way, this is an example of one where we can't really disprove it, and to which we can show a plausible motive for their behavior and reason for a lack of evidence, so it is an okay Fermi Paradox solution from a technical standpoint.
See also Ancient Aliens, They Hide From Us, Zoo Hypothesis. Ancient Aliens.
Ancient aliens is the broader category for the idea that aliens used to be around but have since disappeared. Sometimes through cataclysm, sometimes through war, sometimes to give us time to mature free of further interference, sometimes by ascending to a higher plane of reality. This category isn't problematic because ancient aliens used to exist. Indeed, it is their apparent absence that is the Fermi Paradox, but rather that they seem to now be gone. This general category suffers from two key problems. First is the question of where everyone went, and second is why everyone went there. As we discussed in our recent episode, Fermi Paradox, Fallen Empires, it is nigh on impossible to wipe out a spacefaring civilization, root and stem, and even harder if you're not leaving a conqueror behind who would fulfill that Fermi Paradox just as well. They vanished and so did their destroyer and whoever destroyed them. Solutions range from them visiting Earth in the past and leaving to be wiped out in a war where one side unleashed berserker war machines that killed their enemy, and then turned on their creators too. Whereas we have problems with others like Ascension because it makes you wonder why everyone ascended all at once and why their pets or machines didn't take the chance to replace them after a few million years. Or that they did and we are an example. Their colony here uplifted some primates to near human level for any number of reasons, then they left or died. This is also the category for missing precursors, which tends to fall into the subcategories of accidental precursors, benevolent precursors, neglectful precursors, and abusive precursors, depending on whether or not they were intentionally leaving us behind and liked us, or viewed us as a cheap amusement or irritation.
See also Aliens Used to Visit Earth, Ascension, Berserkers and Hibernating Monsters, Dark Forest Theory, They Hide From Us. Anthropic Principle.
The Anthropic Principle is a foundational concept to science and one of the two principal ways we look at the universe and evidence when details are few and hard to come by. This approach assumes anything we encounter might have its odds of being encountered adjusted by us, the observer, while the Mediocrity Principle discounts the observer. For instance, we would assume that if I encounter someone with red hair, they are a fairly normal and mediocre example of humanity, and by this logic, if we meet an alien with a blue shield, we might assume they were normal too. But it might be instead that aliens with blue shields carry them as a symbolic reminder of a time on their planet when neighbors from distant islands visited from over those blue seas, and might be either friendly or hostile, so a person was chosen to go speak to them and carried a shield for safety. So too, if we met an alien who spoke flawless English, we might assume they were mediocre and that most aliens did, but the Anthropic Principle would instead suggest we are meeting them first because they speak English. They learned it to talk to us. They are not normal for their species, and we encountered them not by improbable luck, but because of who we were. Its partner, the Mediocrity Principle, takes a different view, but critically, both exist principally for contemplation in ignorance, where gathering more data is difficult, and thus is most often discussed with thought experiments like fine-tuned universe, doomsday argument, and the simulation argument or hypothesis. This is most on display with the cosmological Anthropic Principle, which argues that even one intelligent civilization in a universe might be incredibly rare, but only those universes where intelligence has occurred could even notice that it existed. Dead universes go unwatched. We have some reason to believe that even minor changes in various physical constants would make life impossible, leading some to believe our universe itself might be highly improbable. Its key role for the Fermi Paradox is to help us ask if we may be assuming conditions on Earth or with humans are more likely than they actually are, frequently in the context of questioning if intelligence is a common product of evolution.
See also Drake's equation, Mediocrity Principle, Simulation Argument. Ascension.
Ascension is the category of solutions that involve aliens achieving some higher state of being or technological transcendence that basically removes them from visibility or even the universe entirely. This could range from some psychic supernatural phenomena to them discovering how to make a pocket universe of unlimited energy and resources to migrate to, though the most common portrayal is they reach some sort of angelic state of being made of pure energy and moved beyond any mortal vice or motivation. This is entirely possible, of course. Unfortunately, they tend to be common in sci-fi and often badly written, so that their motivations seem nonsensical or hypocritical. And as a quick reminder, you and I are already creatures of pure energy. Mass and matter are one of the categories of energy. Mass, heat, motion, radiation, chemical or nuclear, and dark energy being some of the others, with some overlapping. See our Omega Point Cosmology and Aloof Aliens episodes for further discussion of this category.
See also Ancient Aliens, Technological Singularity. Asteroid Impacts.
Asteroid impacts can devastate a planet and wipe out species, as we believe has happened to Earth before, possibly many times. The asteroid that is thought to have killed the dinosaurs was not particularly large, and there are thousands of bigger ones in our solar system, and likely there were more in the past, as some asteroids have fallen into the sun or planets to strike them or become moons, and other large ones rammed each other and shattered into smaller and less dangerous ones. Indeed, in the early solar system, we believe Earth was rammed by a dwarf planet, causing our moon to form from the debris cloud, and that Venus and Uranus likely had similar impacts. We do not know if Earth has been lucky or unlucky in this regard compared to other systems thus far, and thus cannot say if this is a lesser or major filter. Indeed, it may be beneficial in some cases, shaking up the existing stable ecosystem that can result in hyperspecialization or stagnation. We also do not truly know how much of an effort such impacts have on evolution, as we do not know the state of the ecosystem a few decades before and after the dinosaur asteroid, to know how many of the extinct species were already on their way out, and it is likely to vary by planet and strike intensity and ecosystem.
See also Filter, Jovian Vacuum Cleaner, Rare Earth, Rare Sun. Asymptotic Burnout.
Asymptotic burnout is a newer Fermi Paradox solution that tries to tackle the idea of exponential growth and technological singularities. In math, an asymptote occurs when we have a curve rising ever more steeply as it approaches a maximum, such as energy needed to push an object to light speed, such that it needs to be infinite to actually reach that point. The notion here is that civilizations will realize the eternal growth is impossible and believe it would result in an inevitable collapse, a Malthusian catastrophe or similar, and thus attempts to research a stable point or homeostasis, such as a set and non-growing population. This notion itself is not new and has been one of the major objections raised to the Hart-Tipler Conjecture or the existence of Kardashev Scale civilizations. However, the paper that presents it and names it does give it a more thorough treatment, particularly in the context of the growth of a large city. A line of reasoning might say that the complexity needed to manage a civilization or protect it from destruction might rise superlinearly, which means that if you double the population, you more than double the management or protection it needs. Thus, there is a maximum at which further growth simply becomes impossible to sustain, and you see that and take measures to halt it. The issue here is non-exclusivity, and that it doesn't give a reason not to colonize the galaxy, and that always needs to be a strong one if we're assuming interstellar colonization can be made reasonably practical, because you now need a reason why you are willing to prevent anyone leaving, up to shooting down any ship which tries to leave to colonize a strange new world, and that you are willing to engage in this self-imposed quarantine for astronomically long periods of time. It is possible, of course, but it is hard to argue how a colony being set up thousands of light years away by some breakaways is going to count as unsustainable growth that causes problems to your local system, any more than some folks leaving a major metropolis here on Earth for a ranch in Montana would. And it would be rather hard to imagine any city having a shoot-on-sight policy for those trying to leave, let alone every city that exists now, in the past, or in the future, which is the problem non-exclusivity tends to present to any limit on growth of the voluntary kind.
See also Hart-Tipler Conjecture, Kardashev Scale, Non-Exclusivity.
Before we get back to ways to listen for alien conversations and explore the cosmos, I want to suggest a different way to listen to this show as we explore the future, and that's with top quality audio, like Raycon's everyday earbuds. Raycon's made a name for themselves by providing premium tech products at a great price, not just audio but other home technologies too, like their faucet filter or Magic 180 charging cable with interchangeable magnetic tips to be compatible with your devices. And they have tens of thousands of 5-star reviews, including mine. I've been using Raycon everyday earbuds for years now, and they've provided excellent audio quality even after a lot of abuse. I've accidentally put mine in the washer twice now, and they still work perfectly. Raycon everyday earbuds provide excellent battery life and noise isolating features that have let me enjoy audiobooks or podcasts even when mowing the lawn. And guess what? The best time to grab your Raycons is now. Their early Black Friday sale is here, offering from 20% off site-wide to up to 50% on select items, including 25% off fitness earbuds and 30% off tech kits or the Impact earbuds and Impact speaker. Get an early start on holiday sales by shopping Raycon's early Black Friday sale today. Go to buyraycon.com/IsaacArthur to get 20 to 50% off site-wide.
Aurora Effect.
The Aurora Effect builds on Percolation Theory to discuss how few planets would be traditionally colonizable, how hard the journey there would be to make, and how hard it would be to actually grow and populate and terraform that planet. This builds on the notion that interstellar colonization is hard and tends to only be attempted rarely and on optimal-looking targets, and then that once they get there, many might want to turn around or abandon the goal. This has some plausibility too, as in the story that inspired the name, the colonists arrive and discover simple alien life that infects and kills some of their landing party. Some turn back, some remain, but the colony effort is impacted by this new problem and fewer people, and thus more likely to fail. It is easy to imagine 1.5 million little problems popping up to make a colonial mission harder that were not expected, making success less likely than thought, with no help within a century of travel. Also, that century of travel strongly implies many of the original colonists have died of old age and been replaced by descendants, some of whom may resent the mission and ask to take the ship home as soon as those who want to disembark do, and they can get refueled and turned back. Indeed, even a Methuselah ship, which assumes people are not subject to death from old age, still gives a century of travel to change one's mind, as well as colonists born en route, and those who make the trip frozen might not need more than a few weeks at the new system to decide it was a mistake. The flaw, though, is the same as Percolation Theory. It relies on the assumption that space colonization will be rare and focus on the type of star systems that offer Earth analog conditions and sunlight. Until we actually demonstrate that our usual notion on this show of colonization, that involves fleets, not ships, and goes to every single star, building space habitats, not just terraforming planets, we do not know that this concern about colonization fizzling out is wrong. It is the reason, though, why I tend to assume Gardener fleets will have a ship available to turn around and journey to the system they departed from. Gardener fleets are designed for stopping at each system to drop off colonists and pick up raw materials for the remaining colonists to turn into gear for the next stop, while breeding up more colonists on the journey, and assumes at each stop some will want to colonize the new system and others stick to the life they know on the fleet. But some may want to turn around. likely using a locally fabricated stellazar pushing system to make the journey quicker, and which would also allow colonies further back in the chain to send reinforcements, as we discussed in Rebel Colonies last week. For more details on the Aurora Effect, see our episode Fermi Paradox and the Aurora Effect.
See also Percolation Theory. Axial Tilt.
Axial tilt of a planet is one of the lesser or minor filters that contributes to the wider rare Earth Great Filter. Earth is tilted relative to the Sun and our orbital plane, meaning the intensity of light on any spot on the planet varies by time of year, and the degree of tilt governs how much that variation is. Thus, axial tilt is a strong factor in how severe that planet's seasons are, and it is very likely our moon has impacted that tilt by being a stabilizing force, keeping Earth's tilt to roughly 23 degrees, while some models show it varying by up to 85 degrees without our moon. Polar circles are 23 degrees and places where the sun will not rise or will not set for long stretches. The longer, the closer to the pole you are. So an 85-degree axial tilt would mean a planet would have its Arctic Circle stretching nearly down to the equator. This does not mean it's always cold, rather it means the place most folks live on Earth now would instead be having durations of eternal summer and sun for many weeks, followed half a year later by a winter of eternal darkness for several weeks. This does not necessarily prevent life or even complexity, but such severe seasons would be a complicating factor. What's more, axial tilt can vary with time. We believe Earth shifts by about 2 degrees for the Milankovitch cycles and other variations associated like axial obliquity and precession, and perturbations from larger planets like Jupiter.
See also Filter, Great Filter, Jovian Vacuum Cleaner, Large Moon Needed, Rare Earth, Rare Sun. Berserkers and Hibernating Monsters.
One popular explanation for the Fermi Paradox is that the galaxy is littered with sleeping machines or monsters that pop out to eat technological civilizations. This draws its name from the Berserker stories by Fred Saberhagen, which feature machine intelligences which wiped out their own creators and are intent on getting our other biological life too. Sometimes these are rogue von Neumann probes or terraforming machines gone astray, sometimes leftover superweapons from a war who killed the enemy, then turned on their creators. Most often fiction, they are a predator in the darkness with indistinct motives, as we see in Lovecraftian cosmic horror, and indeed many pre-science fiction tales of dread. The Reapers from Mass Effect, Borg from Star Trek, or Shadows from Babylon 5 would be examples in popular fiction, and fleshing out their background and motivations only tended to make them seem less interesting as bad guys. And I think that's because their strategy's flaws start poking through. It makes people wonder why they are killing off intelligent life, how they missed Earth, why they wait till you've got spaceships to attack, and why they hibernate and do nothing in the meantime. It then runs into non-exclusivity and the issue that the galaxy is not the same thing as the universe, so that a galaxy-spanning sleeping predator should have been displaced by some expeditionary force from some other galaxy that did not twiddle its thumbs for million-year-long halftime shows. See our episodes Sleeping Giants and Gods and Monsters for further discussion.
See also Non-Exclusivity, Our Galaxy Isn't the Whole Universe, Technological Singularity. Black Hole Farming.
Black hole farming, as discussed in the first episode of our Civilizations at the End of Time series, refers to civilizations that use black holes as their main power source, either by methods like the Penrose process for dumping mass into existing black holes and getting energy from them, or via Hawking radiation. These methods are on an order of 100 times more efficient with mass energy than fusion. Critically to the Fermi Paradox, it implies a lot of civilizations switch to use natural or artificial black holes as their power supplies, and also because black hole lifetime is so insanely long, dumping matter into them and moving to them basically serves as enormous batteries or bank vaults for after all the stars burn out. There is no advanced technology needed for feeding or moving existing black holes, or tapping the power released during feeding, or from the later stage high-intensity Hawking radiation. So a civilization might create a sequence of black holes, each just a bit more massive than the last, each having something like a trillion-year period where they were giving off nearly a gigawatt of power, and just skip over to the next one as each, for lack of a better word, blooms. This allows biological civilizations to carry on for quadrillions of years at least, and post-biological ones far longer. and it is the reason why we tend to assume that civilizations have a motivation to harvest an entire galaxy's worth of mass, stars and nebulae alike, since they can run very nearly eternal empires this way.
See also Aestivation Hypothesis, Post-Biological, Rim Migration. Boltzmann Brain.
A Boltzmann brain is a hypothetical mind which assembles at random from particles bumping into each other. This is incredibly unlikely in our universe compared to evolution, but may be more likely in realities with different physics. We discussed this more in our episode on Boltzmann brains and the Anthropic Principle. What is more pertinent to the Fermi Paradox, a Boltzmann brain that assembled in some reality would be surrounded by empty nothingness, not a planet, relatives, predators, prey, or food, and statistically is unlikely to even have sensory apparatus, and thus might go insane and hallucinate a reality. Reminiscent of the simulation argument, but without a simulator, this is more of a concept that reality is just a dream, and thus nothing in it has to rigorously make sense or be entirely consistent, like apparent paradoxes. As a Fermi Paradox solution, this works just fine, though strongly implies, to you anyway, that I am a voice in your head, and nothing you see is real or indicative of how the real universe works, and that you are madder than a hatter.
See also Simulation Argument. Carbon and nitrogen ratios.
Not including dark matter, most of this universe is hydrogen and helium and started off that way. While stars fuse hydrogen into helium, most of the helium started forming about 20 seconds after the Big Bang, when the universe better resembled the core of a giant star. And after a few minutes we were left with about 7 protons for every neutron in existence, and most of those neutrons paired up with another and 2 protons to form a helium atom, with some in deuterium, helium-3, or short-lived tritium, and a tiny fraction, around a billionth, as lithium-6 or 7. It was essentially a ratio based on how many nucleons, or protons and neutrons, were in an atom, and that nothing with 5 or 8 nucleons is stable. That's the original universe, 12 atoms of hydrogen for every helium, which being more massive and with more nucleons is where about a quarter of the mass ended up. As helium plus a trivial billionth in lithium, no oxygen, carbon, or nitrogen existed. That took stars forming, which took another quarter of a billion years. Stars fuse hydrogen into helium, but our sun's helium content is almost entirely from atoms that existed since the Big Bang, not stellar fusion, and helium can also be fused into heavier elements as bigger stars age. One of the major fusion chains is the CNO cycle, short for carbon, nitrogen, oxygen, and this results in oxygen, carbon, and nitrogen being the 3rd, 4th, and 7th most abundant elements, at 10,400, 4,600, and 960 parts per million respectively, and making up most of the remaining mass of the universe that is not hydrogen, helium, neutrinos, or dark matter. Nonetheless, that's very scarce and has been rising with time. The rate isn't quite linear to age, but if you went back to when the universe was half as old, you would find about half as much of those elements, and yet they are critical to life and critical to having quantity. Oxygen is the most plentiful and heaviest of those 3, thus least likely to blow away under solar wind from an inner region of a solar system. It also reacts strongly and bonds to nearly everything, unlike helium which bonds to nothing, and as a result it is usually the first or second most abundant element on any rocky planet or moon or asteroid. Water and most rock is mostly oxygen by mass fraction. Carbon does better than nitrogen, there's 5 times as much of it too, but in the end both are not terribly abundant in our inner solar system, and likely that is a fairly universal condition, so that many early worlds would not have enough to have made life very probable, but as time goes on it becomes more common. And so too, it becomes more probable that you would have planets in the Goldilocks zone of a system that were not just abundant in water, but also in carbon, and able to have nitrogen-rich atmospheres and abundant enough in both to support geological, hydrological, and biological cycles that help make sure life on Earth has a dense and accessible supply and in the right ratios.
See also Critical Element Scarcity, Goldilocks Zone, Metallicity. Colonizing Is Too Dangerous.
Colonizing Is Too Dangerous is a subcategory of late filters of the Fermi Paradox that focus on reasons why you might be able to colonize space but choose not to. This is an interesting case as it has an example of convergent behavior to explain why all civilizations might do it, and thus it wouldn't be a violation of non-exclusivity. The reasoning goes that in the absence of faster-than-light travel, you cannot really have a cohesive interstellar empire of any real size, and thus you decide the best plan is to limit yourselves to the K1 or K2 scale, which is still beyond enormous compared to any empire we have ever seen, and you just don't let people fly off in colony ships. Shooting down fleeing ships is insanely easy and foolproof. They cannot outrun your missiles, which need no fuel to slow down, and they do if they want to colonize anything rather than die in space when they run out of resources. We have discussed that in our space warfare episode, so you can plausibly maintain this sort of self-imposed quarantine indefinitely from a technical perspective. From a political or social perspective, it gets harder, but your core selling point is that adding colonies near you doesn't give you much more than an enemy in embryo, as they will get divergent, and instead of having empty space all around you, you now have potential enemies. Friends and allies maybe too, but enemies, ones with doomsday weapons, or who might get lazy and unleash a von Neumann swarm of berserkers. In this regard, while it has its weaknesses, especially as a long-term reason space doesn't get colonized even over millions of years, I do consider this one of the stronger Fermi Paradox solutions.
See also Berserkers and Hibernating Monsters, Late Filters, Non-Exclusivity. Colonizing is too hard.
When it comes to reasons aliens might be visible to us, the idea that they are rare because of various filters is common, but some come after where we are at now, the late filters. And perhaps the most classic, dating back to Enrico Fermi himself, is that colonizing space is simply too difficult to ever be practical. We have many episodes devoted to that, the most recent being The Last Planet and Colonizing the Galaxy, and I feel the evidence favors space colonization being practical. But until the day that we not only have an interstellar colony, but several who themselves have begun sending out colony fleets of their own, we do not know if this is a lesser filter or some great filter. That maybe many get to where we are now and just never colonize much beyond their solar system because little is gained and much spent. And this is a critical concept to the Aurora Effect and Percolation Theory, which tend to assume interstellar colonization is at best a marginal affair. Obviously, I disagree rather loudly and about once a week for nearly a decade now, as more than half our episodes speak to how space travel can become practical. Not exactly a shocking viewpoint coming from the president of the National Space Society, I suppose. For further explanation of why, see episode 1, 2, 3, 4, 5, 6, 7, 8, 9, and really nearly every episode up through today.
See also Colonizing Is Too Dangerous, Great Filter, Late Filters. Compounding filters.
Not all filters of the Fermi Paradox are great filters. Some, like a planet being in the Goldilocks Zone, are decently likely, while others, such as multicellular life or photosynthesis evolving where life already exists, seem likely in most cases. However, the cumulative and compounding nature of these sorts of lesser filters can stack up. In our original Fermi Paradox Compendium, we walked through an example of compounding filters to show even a number of lesser filters could make a single example of life anywhere in this universe improbable. In simple form, if we assume 10 lesser filters, which were each just a 50-50 coin flip odds of passing, just half pass for each, the odds of making it through each of those is 1/2 to the 10th power, or just under 1 in a million. In that episode, we listed 50 such filters that were commonly proposed, most of which were viewed as worse than 50-50 odds, and which, if true, would make intelligent, spacefaring life less likely than not to exist anywhere in the observable universe. Many proposed great filters can also be decomposed into a collection of lesser filters, such as the rare sun or rare earth great filter, where the former might include dozens of factors like star lifetime, brightness, whether it is binary or not, and more listed under that entry.
See also Drake's equation, filter, Goldilocks zone, great filter, late filter, rare earth, rare intelligence, rare sun, rare technology. Cosmic collectors.
The Cosmic Collector Hypothesis derives from our Alien Civilization series, where we tried to deduce what might be indicated about our visitors if sightings were accurate. While somewhat tongue-in-cheek, the hypothesis suggested that if a prime directive of non-interference exists and is enforced in our area of the galaxy, it likely is a quarantine that is only enforced to the degree seen as reasonable and necessary, like enforcement of most regulations with limited resources. Such being the case, it would be believable that visits to Earth might be by elements who have ramshackle spacecraft, prone to crashing or having their stealth systems fail, cannot rely on support from local forces, which might shoot them down or arrest them if they saw them, and which might have a lot of maintenance issues with ships and cloaking devices. Our notion here goes to our usual rule about alien invaders, that Earth doesn't really have much aliens would want in terms of raw materials, and that only biological and cultural data unique to Earth has value. But you do not need to abduct humans for DNA. You can abduct a mailbox or vending machine and lift the DNA of many people off the letters or coins. Many other Earth-unique things could have been collected before humans got technology, as we always assume aliens knew about Earth being inhabited nearly as long as they themselves have been around, or could be collected more easily once Earth joins the galactic community after all Prime Directive protection passes, or just sneak in and download Wikipedia or rent a house in an area with good broadband and where a comm laser to a satellite in space would go unnoticed among all the other traffic. So we posit that the only underground physical trade Earth and other primitive planets truly has is the sort of collectible items that people might really want originals of, and that the galaxy probably has a large black market for pre-contact alien literature and art. In other words, the aliens show up to snatch up copies of first edition comic books and novels. As we also proposed in that episode, conflicting government conspiracy theories might result from many unrelated and tricksome alien smugglers having allies on the planet they duped into helping them, such as Smuggler A telling someone in the Defense Department they represented alien freedom fighters and were offering secret help, but needed you to ignore their radar signal and keep them quiet from your own government, which was infiltrated by the local evil Galactic Empire. Smuggler B lies to the security guards of the Smithsonian that they need covert access to treasures for Earth's safety, while Smuggler C might have told the FBI that they need to help him salvage and keep secret his crashed ship and dead co-pilot, and without tipping off the space mafia who had infiltrated Earth, and so on. The alien quarantine force near Earth knows this stuff happens, but maybe takes some bribes if it's kept minimal, or they just don't have the resources to stop such minor infractions when they know Earth is going to be brought into the galactic community soon anyway, and see our own sci-fi and know we already talk about aliens all the time. So why bother with strict enforcement?
See also Ancient Aliens, Grabby Aliens, Prime Directive, Quarantine Hypothesis. Critical Element Scarcity.
Life on Earth is principally made of 6 elements: hydrogen, oxygen, carbon, nitrogen, calcium, and phosphorus. Phosphorus is the least of the 6, but still on that top 6 and critical to life as we know it, with no clear substitute available that's more abundant. In our episode The Phosphorus Problem, we explored the origin of phosphorus and its critical role in life and why it's so rare as an element. There are other elements in us that are less common, and critically, were less common when the universe was younger, but there may be millions of types of life that don't use water as a prime solvent or aren't based on carbon, but some rarer element that are simply too scarce to have had a chance to produce life yet, or need some other rare element in a tiny but vital role, like phosphorus. Life from universes with slightly different physical constants, or where life formed later in the universe's overall nucleosynthesis processes, might operate on very different chemistries.
See also carbon and nitrogen ratios, Drake's equation, metallicity, rare earth, rare sun. Dark Forest Theory.
Dark Forest Theory was popularized by the novel of the same name, but covers a number of order Fermi Paradox solutions that generally fall under our Berserker probe heading and is a quiet aliens approach. See our episode Dark Forest Theory and Hostile Galaxy for details, but the loose idea is that the galaxy is a dark and dangerous forest full of predators, and the last thing you want to do is shout and draw attention to yourself in such a case. This is one of our examples of popular theories for the Fermi Paradox that sound completely reasonable on first inspection, but can be set aside as essentially non-viable. The reason is pretty straightforward. It is not a good idea to draw attention to yourself in such a situation, but it is assuming first that nobody has seen you already, and second, that if you hold still forever, you won't get eaten. In practice, you are often better off lighting a fire and getting some sticks sharpened, And regardless, you are going to starve to death if you keep standing there, assuming nothing happens to come close enough to see you and eat you in the meantime. This inactivity policy is tantamount to suicide on galactic timelines as a result. More importantly, not only should any civilization figure that out pretty quickly, but they would also be aware that their planet has been giving off techno-signatures for centuries, and bio-signatures for billions of years, and that any civilization that could send an armada their way could also have sent probes if their telescopes weren't good enough to spot them, and that this is something they would almost certainly have done. And while some civilizations might hide indefinitely this way, in a silent universe, we would assume many would not, and thus some would be talking out loud, and once they did, others would shrug and say yes, especially if they were getting name-specific messages, like sending a beam to Earth that had a pulse built in every 24 hours and 365 days, which isn't screaming into the darkness so much as tapping on someone's dining room window and waving at them at the table. So this is popular but just has too many flaws to be a probable one.
See also Berserkers and Hibernating Monsters, Non-Exclusivity, Techno and Bio-Signatures, They Hide from Everyone. Detection windows are few and short.
A critical factor of Drake's equation and late filters is not just that few civilizations might arise in a galaxy, but that they might not last too long, thus their detection window is dim and short. We can hypothesize civilizations expanding in the galaxy and giving over large portions of one star's energy to a huge beacon that can be heard even across a galactic supercluster, as they presumably have millions of stars and at least many thousands of years to build such a thing. However, an Earth-scale civilization, or one just a bit bigger and more advanced that died in, say, 2397, would only have had 500 years in which radio broadcasts were occurring. However, if they only broadcast for 500 years themselves, and even at their peak could only have heard themselves, or a duplicate, about 1,000 light years away, then the galaxy could have had literally a million of these civilizations arising over the last couple billion years, with only one or two typically existing at the same time, and scattered over the whole galaxy, not the tiny region of 1,000 light-years radius in which not even 1% of the galaxy's stars existed in. See our episode Fermi Paradox, Whispers in the Night, for a deeper dive on these odds and implications.
See also Drake's equation, late filters, SETI. Drake's equation.
A core concept to the Fermi Paradox is Frank Drake's equation contemplating how many alien civilizations might be there in the galaxy for us to listen to based on a probabilistic argument. We detailed it and its flaws in our episode on Drake's equation, but in short form it contains several variables whose values can be guessed at for an approximation of how many extant technological civilizations are around and transmitting signals SETI might hear. Those areas follow: the rate at which stars form in our galaxy, the fraction of stars that have planets, the average number of those planets with potential habitability, the fraction of habitable planets on which life actually develops at some point, the fraction of planets which develop life, which is also intelligent, the fraction of intelligent life which develop technology, which is detectable to us by its signature, and lastly, the length of time which that technology is releasing said detectable signatures. You can insert many different values for those, and we have a growing idea how many stars have planets, and it's probably most of them, but it highlights a common problem the equation tends to produce in my experience. Folks see the factors we know, and see that they are probably 1 in 10 or maybe even better, but not less than 1%. And assume that the unknown variables are probably likewise, and thus thousands if not millions of civilizations might be around in our galaxy. The problem there is that we don't have any idea of that value for some of those variables, and if just one of those filters was a big one, lottery odds, then life is ultra rare. And the great filters approach to the Fermi Paradox of concepts like rare Earth are that a more complete Drake's equation with all the relevant filters as variables, many dozens, looks like something where intelligent life isn't very likely at all.
See also compounding filters, great filters, rare Earth, rare Sun, SETI. Dyson Dilemma.
The Dyson Dilemma is an extension of the Hart-Tipler Conjecture that reasons that it is possible to colonize interstellar space, that it is desirable, and that the de facto state of any civilization around a star is to work to either encompass it completely for power collection or to disassemble it for its resources. That in any given scenario, a star left sitting there burning and unused should be maddening to any civilization subject to entropy. And thus the big question we should ask ourselves when looking up at the night sky isn't where all the aliens are among all those stars, but why there are any stars up there still visible for us to see. You can see that episode, or its revised version 2.0, for a deeper dive and for discussion of possible exceptions, like if they have perpetual motion machines, multiverse travel, or instantaneous FTL communication, as well as reasons you might not build Dysons, or why they might look different than expected, as we covered more recently in our episode Searching for Dyson Spheres. Critically, such expanding waves of K2 civilizations turning into Kardashev 3 civilizations should be visible not just throughout our galaxy, but as far away as we can see, so that any civilization in a couple billion light years that's older than the light traveling to us from there should be blatantly visible. We see none, and that's the dilemma of seeing no clusters of Dyson swarms or like objects in regard to the Fermi Paradox, or the Dyson Dilemma. As a bit of channel trivia, to further crowd out this already super long episode, the Dyson Dilemma is the name of the second episode of this show, and one I've always regretted because it is named in regard to Dyson spheres, but not only is the name better known for a vacuum cleaner brand, but Freeman Dyson himself, who the spheres are named after, is best known for his work on the game theory problem known as the Prisoner's Dilemma, which really messes up search results for the concept. I did the episode after some thoughts and discussion on New Year's Eve of 2014-15 at my friend Jason Keeler's house over a board game called Acquire, whose playstyle inspired the discussion, with a few other friends including my future wife Sarah, and it was the first time she and I ever had a long conversation, in fact. We had another one some months later on Quantum Resurrection that I think moved us from casual friends just above acquaintances to good friends. Sarah and I started dating 4 years later right after Jason's own wedding, which we were both in, and the board game Acquire was the one we played at my bachelor's party right after the outbreak of COVID. Our original Fermi Paradox Compendium was done in response to the original episode, as folks asked if I could explain why each of the various well-known Fermi Paradox solutions did not function well under the Dyson Dilemma, and in point of fact with the hope someone would poke big holes in it, as I always liked the idea of a more classic space opera universe full of aliens anyway, and 9 years later, here we are. Also, I have yet to hear a rebuttal to it that anybody else seemed to find convincing, besides the presenter of said rebuttal. I'll rebut rebuttals when I hear them, if I can, but I don't tend to trust my neutrality and tend to encourage others to take that same approach. Judge a given solution you like by how convincing other people find it, not just yourself. It is one of several solutions I either developed or formalized, usually attached with why they were wrong, but the only one I really claim personally since it's got such a big connection to the show's development and my own personal life.
See also FTL faster than light travel, Hart-Tipler Conjecture, perpetual motion machines, multiverse and alternate reality aliens. Earth and humans are boring.
One common reason given for why aliens might exist and have fantastic technologies, like FTL, but never come by Earth, is that they regard our pale blue dot as a mundane and boring planet populated by equally boring and primitive savages. Earth is insignificant and best described as mostly harmless. It makes for some good science fiction, and it never hurts for us to have some humility and consider that in the grand galactic space opera, we are bit players, not where the heroes come from, not pivotal in any way, whose planet might be mentioned, if known at all, only in the way people tend to mention Kansas, that boring place they flew over. Except millions of people visit Kansas every year, and in a big galaxy there might be lots of more interesting places to travel to, but that just scales up from our own planet. It's got tons of tourist spots everyone knows, and millions more most of us have never heard of, but still get visited a lot. so the idea that Earth is impossibly boring to visit just doesn't seem plausible. The second half of that is that humans are boring or inconsequential, and the same reasoning applies, though we also have the possibility that most aliens are hyper-intelligent post-biologicals or super-evolved organisms who view us as little more than pets or even ants. This doesn't hold too well under non-exclusivity either, as we have people who visit Kansas and people who study insects who would love to talk to them. Intelligence does not, that I've noticed, tend to encourage people to less curiosity, and most of us talk to our pets, or even our houseplants, and there's no special reason to assume no aliens do the same. So while it's a tastefully humble stance, it isn't a very good Fermi Paradox solution.
See also post-biological. Filters.
Filters of the Fermi Paradox are various hurdles life is thought to need to pass to get to technology or conditions for a planet or star system to be habitable. They principally are for discussion of the rare Earth hypothesis and its cousins like rare sun or solar system, rare intelligence or technology, or late filters, ones which we have not already passed through but might get us, like artificial intelligence. It is assumed Earth and humanity has already successfully passed through the other filters. On this show, we classify filters into lesser filters, minor filters, major filters, and great filters. A lesser filter is a condition we think most times gets passed through successfully. For instance, most stars are as long-lived or longer than our Sun, so a star dying before life had 4 or 5 billion years to evolve would be a lesser filter, as most pass. Minor filters are those most fail but many do pass, and we tend to treat this as less than 50% but more than 1%. A planet being in a habitable zone and massive enough to have water would fall into this category. Major filters are those where success is rare but hardly unheard of, less than 1%, and maybe only a few in a million succeed, and this would include a rock in space being big enough to even have an atmosphere, as there are millions of minor planets in our own solar system. In a system of millions of such rocks, many will be big enough, and in a galaxy of trillions of big planets, any lone major filter still means millions of successes. For this reason, we either discuss great filters, those things so incredibly unlikely that they are like winning the lottery, or less probable than even that, or compounding filters, the effect of many weaker filters but stacked in a row.
See also compounding filters, great filter, late filter, rare Earth, rare intelligence, rare sun, rare technology. FTL, faster than light travel.
We believe that traveling faster than light is impossible under known physics, but it is a staple of science fiction, and of course, we never know what impossible things might turn out possible where science is concerned. However, FTL has a couple of problems with the Fermi Paradox. First, it tends to imply time travel is possible too, paradoxes and all. And second, it is an example of a technology that only exacerbates the Fermi Paradox if available. Not only do many Fermi Paradox solutions rely on space travel at sublight being very hard or impractical as they are reasoning aliens don't colonize other stars, but it expands the regions we need to consider. Our big issue is trying to figure out why nobody in this galaxy rose before us and colonized Earth, as it only requires a few million years of a head start to colonize a whole galaxy ahead of anyone else who might evolve there. Throw in FTL and you need to expand that explanation from a galaxy, or maybe even a supercluster, up to the entire observable universe, and even beyond that. And now whatever handwave a given theory has for why most civilizations don't do some policy that would make them visible to us not only needs to cover 1,000 hypothetical civilizations here, but the 1,000 in each of the trillion other galaxies in our Hubble volume and the regions near it, or even more. 1 in 1,000 becomes 1 in a quadrillion, a big shift in odds. So regardless of whether or not it is possible, it is almost never a good explanation for the Great Silence. See our FTL series for more explanations of how FTL might work or why it should not.
See also Great Silence, Perpetual Motion Machines, Multiverse and Alternate Reality Aliens. Solution exacerbates the Fermi Paradox. Time travel. Galaxy type and stability.
One of the categories of filters that doesn't fit well into the rare sun or rare earth categories is the idea that some galaxies may not only have regions that are rough on life, but may be entirely hostile or have sterilizing events like quasar eruptions or black hole ringdowns that just kill off any non-technological species that can't predict and fortify against the event. This is not likely to be a strong filter in terms of existing galaxies. Many might be hostile in whole or part, but probably not an overwhelming majority. However, it is very likely to apply to older galaxies in general, which were more active in terms of quasar and quasar-like events, and thus may be the reason we don't see ancient empires. They just were far fewer and rarer until relatively recently. The rate and time for when galaxies become plausibly habitable is fairly critical to concepts like Grabby Aliens or the Dyson Dilemma, since they contemplate Kardashev 3 and 4 scale civilizations as the eventual fate of any civilization which manages to get into space while their region is still empty of other intelligences.
See also Dyson Dilemma, Grabby Aliens, Rare Earth, Rare Sun, Recent Galactic Catastrophe or War, Stellar Neighborhood, Time Elapse Argument. Goldilocks Zone.
The Goldilocks Zone is another term for the habitable zone of a system and generally means where liquid water is possible on the surface of a planet, even if more widely it's supposed to be those areas that are not too hot or too cold for life. The name derives from the story of Goldilocks and the Three Bears, which, if you're not familiar with it, charts the activity of a nasty little girl who breaks into the bear's home and eats their food and sleeps in each bear's bed before they catch her and eat her instead. And of course the big problem here is that we don't actually know what is too hot or cold for life, and bears, for instance, are generally going to thrive in a colder environment better than equatorial lizards. Another key thing to remember is that the habitable zone size is based off the star's brightness and age, so they migrate with time, and many planets that might have begun habitable and warm early on might be scorching desert infernos not even the sandworms of Dune would tolerate before that world was old enough for intelligence to have evolved. Nevertheless, for all the uncertainties of what is habitable, it guides our basic hunt for Techno and Bio-Signatures, particularly the latter, not because we are sure other life can't exist, but because we know we do exist and hunt for parallel cases as the low-hanging fruit of SETI.
See also SETI, Techno and Bio-Signatures. Grabby Aliens.
As our contemplations of possible space colonization techniques and spaceship drives expands, it can often feel an inevitability that most civilizations, at our point, successfully colonize space and keep moving outward. So they rapidly become loud aliens and stay that way to the end of the universe, simply growing bigger till they run into cosmic voids or other mega-civilizations. As such, it works from the standpoint that whatever firstborn civilization in our region of the universe successfully gets into space is going to claim space expanding out from them at some decent fraction of light speed, whether it's 1% or 99%. And that every such civilization is going to reach that optimal ship drive technology and same maximum colonization speed, whatever it is, in a relatively short period of time compared to the galactic or evolutionary scale, and have an expanding bubble that eventually runs into other bubbles, and slightly more frequently into smaller bubbles or ones with relative primitives on it, which they may or may not incorporate or wipe out or slice a reservation out for. We assume no FTL here, so this is not a unified civilization, just an eternal wave of colonies growing and having someone on them decide they want more elbow room and leaving to settle an empty system. The Grabby Aliens term comes from a paper by Robin Hanson a few years back, who also coined the term Great Filter and has been a long-time proponent of the idea that alien intelligences are ultra-rare is our strongest Fermi Paradox solution. And again, the idea wasn't new, but the term really grabbed media attention. And I could wish it was a different one because it kind of implies greedy or locust-like behavior rather than giant civilizations who just keep spreading out to dead and lifeless worlds as opportunity and desire permit, same as early human tribes probably did. What the paper did that was new was to mathematically model this approach and pick some speeds and expansion rates, calculate how often such civilizations arise in order for us to be likely not to have seen any such civilizations yet ourselves, and not be a freak anomaly. The numbers are not exactly arbitrary, but how fast everyone is spreading out really controls the range of results, and what we find is that for expansion rates of about 80% light speed, the number of such civilizations that exist, or will soon come to exist, in the observable universe is on an order of 1,000 to 10,000. Which sounds like a lot, but is tiny compared to the number of galaxies. As such, your typical Grabby alien civilization would have an average of several million galaxies to call their own when they are bubble maxed out. And for that reason, we do give it the status of being Kardashev 4, as the jump is in the same range as we get for K1, K2, and K3, being a planet, star, and galaxy respectively. And that number is a matter of probability, as is that we are part of that group, a future Grabby alien, but probably on the later side, with nearly every Grabby alien arising in the next few billion years at latest. See our episode Grabby Aliens for a deeper dive, as well as some of the issues or objections raised. And again, this is the camp I personally tend to be in, though it is not without its flaws and others have their own strengths too. If true, it means that humanity might be a later Grabby alien civilization, or one of the first, but the odds favor us having not just this galaxy, but thousands of others to colonize before running into anyone else. It is also likely that Hubble expansion would see a lot of smaller chunks of space never reached by any one of these bigger bubbles, so you might have millions of latecomers who are limited to a smaller region, a mere galaxy or two isolated by Hubble expansion in many billions of years, which is hardly a tiny amount of space.
See also Dyson Dilemma, Hart-Tipler Conjecture. Great Filter.
Great filter is a term coined by Robin Hanson, an economist who's been one of the most active and long-time proponents of the general rare earth, sun, intelligence, and technology camps of the Fermi Paradox that generally arises from the Hart-Tipler Conjecture. The notion here is that life will surely arise and get spacefaring and expansive, if it is possible, often enough that even just one example in a galaxy will see that whole galaxy colonized inside a million or so years, and maybe beyond, as in the Grabby Aliens scenario, which is the default perspective of this show. As a result, since this doesn't seem to be the case, there are probably tons of filters that prevent most from reaching the point we are at now, or one single great filter, something so unlikely to be passed that you have better odds of winning the lottery or being struck by lightning. Many have been proposed, but our ability to determine the strength of their filtering is limited at this time. See our Great Filter series for a discussion of the candidates in more depth. Some great filters would break down into a number of compounding lesser filters of various individual strength, such as the rare earth hypothesis is usually assumed to be, that simply add up to a great filter. And of course, the existence of one great filter does not mean others don't exist, or that many unrelated lesser filters might apply.
See also Dyson Dilemma, Filter, Grabby Aliens, Rare Earth Hypothesis, Rare Intelligence, Rare Sun, Rare Technology. Great Silence.
The Great Silence is the observed condition of the universe by modern astronomy and SETI, the search for extraterrestrial intelligence, that we do not see anyone, and the basis for the Fermi Paradox. The Great Silence is also often used as another name for the Fermi Paradox, named for the inability to detect any extraterrestrial signals or presence of any loud aliens.
See also Loud Aliens, Quiet Aliens, SETI. Hart-Tipler Conjecture.
The Hart-Tipler Conjecture is a modification to the original Hart conjecture by Frank Tipler in the 1980s to include options for machine intelligence, von Neumann probes, and other pathways for expanding into the galaxy beyond faster-than-light travel or generational arc ships. The original Hart conjecture by Michael Hart in the 1970s, coupled to his coining the term the Fermi Paradox, is the first officially proposed solution as a result, and reasons that since life is compelled to expand and grow, and that any life form that does not will be replaced by some successor or fraction of their civilization that does favor growth, that an unpopulated galaxy can only be because interstellar space travel is nigh impossible, or that technological life emerging is ultra rare, and we are the first local example. The inclusion of machine minds by Tipler makes the case for practical expansion even more robust. As it is essentially solution number one to the Fermi Paradox, there are many attempted caveats and rebuttals to it. perhaps the most common being that civilizations wreck themselves faster than they can grow, or some similar late filter, or they find some way to circumvent the biological imperatives for growth. The latter would seem doable, though then relies on the idea that there is a strong logical reason to do so, one that might be so compelling as to override non-exclusivity, so that everybody finds this reasoning compelling, or those who do not tend to die, or that very nearly everyone is convinced. Most of those who are not die, and the relative few remaining just aren't common enough to be seen yet. The Dyson Dilemma, presented in the second episode of this show, can be viewed as an extragalactic add-on to the Hart-Tipler Conjecture.
See also Dyson Dilemma, Non-Exclusivity, Resource Hoarding. Hermit Shoplifter Hypothesis.
The Hermit Shoplifter Hypothesis has its origin in our show's livestream Q&A from this summer, where the topic of neurohacking came up. The notion is similar to Fermi Paradox concepts involving civilizations converting into virtual reality environments, falling to psychic poisons, or rim migration, but borrows a bit for each to explain the behavior. The notion goes that civilization functions principally to help personal survival, and that as technology improves, things like AI, VR, 3D printing, mind uploading, or nanobot regeneration techniques, digital data storage, and other technologies not only makes survival less dependent on others, but begin making civilization itself dangerous to be near. Any lone lunatic begins having access to doomsday weapons, while any person can live indefinitely, either post-biologically or simply regenerated by nanotech. Their greatest threat is other people, and so they flee civilization in a personal spaceship able to completely repair itself and them, with a dense library of knowledge and entertainment, and tended by robots and AI. They can easily remain on the outskirts of an expanding civilization should that occur, able to pick up resources from any system they pass, but may ultimately decide the safest place to be is in the ultra-empty space such as that between galaxies, where Hubble expansion will eventually isolate them from any possible threat. They themselves probably live in various virtual utopias, so the outside scenery is not of concern to them except for resupply or threats. This becomes a Fermi Paradox solution if various technological time bomb scenarios tend to wreck civilizations, and because in the early spacefaring civilization era, resources are so plentiful and automation so great that many billions of people could easily stash a billion years worth of fuel in some giant personal spaceship without barely scratching a single star system's resources and head out to the galactic rim and beyond. They are more intent on getting out of danger than maximizing their resource hoard, since sticking around to gather another billion years worth of personal fuel carries some risk that fleeing at that moment does not, and likely there is a personal calculus as to how much resources can be grabbed, the practical half-life of any resource supply, no matter how big, and a host of other considerations, like being seen taking off with so much resources that others come after you for spite, piracy, or a sense of ethical outrage at your act of grand theft nebula. The obvious flaw is the assumption that either every single person in a civilization does this, and thus violates non-exclusivity, unless those who don't flee are wiped out by some inevitable civilization-obliterating event.
See also Psychic Poisons, Rim Migration, Technological Time Bombs, Virtual Reality Utopia. Inevitable Intelligence Implosions.
This somewhat broad category covers solutions that imply intelligence itself will inevitably find a way to destroy itself, and can range from everything from the Medea hypothesis to technological time bombs, or us inventing technologies that make us lazy or stupid or prone to nihilism or ennui. The key difference between this and others is that it covers any scenario where the destruction becomes effectively guaranteed once high intelligence is achieved, though it can also be a blanket great filter option for any number of self-crafted doomsdays, from AI to environmental damage or doomsday devices.
See also Neurohacking for Happiness, Nihilism or Ennui, Psychic Poisons, Technological Time Bombs, Virtual Reality Utopia. Interdiction Hypothesis.
Interdiction is very like zoo hypothesis except different in motivation, Civilizations don't expand faster and slam into each other because species agree to large buffer zones, and they don't talk to other low-tech races because they've agreed not to, on the grounds they don't want their potential rivals or enemies poisoning the primitives' minds about them, and they generally think conflict is best avoided by avoidance. Occasional minimal violations by rogue actors may be the source of apparent UFO sightings on Earth. The philosophy is to stay away from aliens. You can never wipe them all out, and everyone will know if you try and reply in kind. And you are always surrounded on all sides by potential enemies who have every motivation to attack you back if you try it. So it's easier to expand to an agreed size, leaving buffers, and get along with minimal contact. Everyone agrees to keep themselves pretty small, so nobody has a motive nor ability to go to war. And since their own descendants are likely to be pretty alien if divorced far enough by space and time, they may see no reason to go butt heads with actual aliens just to make room for distant mutant cousins. This one doesn't assume any particular alien motivation besides caution, which does not violate exclusivity, since we can assume, like curiosity, that caution is a trait probably shared by all technological civilizations. There is also a good reason to enforce it, and it's easier to enforce it with all that buffer space rather than direct borders. You still have the issue of newly emerged spacefarers getting angry nobody gave them technology and resenting that they were left to face endless disasters when a few easy bits of help would have saved untold millions, but the counter-argument seems a little bit less smug maybe. We didn't think you needed to be left alone because we were too high-minded to interfere with primitives, even to save them from asteroid or plagues, but rather we agreed to this treaty. It's been around for a very long time before us, and even if we didn't think it was a good idea to keep it, we don't want to suffer the consequences of violating it. This rubs some folks the wrong way because they figure we ought to be able to talk to anyone, be friends with everyone, but interdiction doesn't say you can't chat a bit, just that it's kept distant and minimal. And realistically, getting along and tolerating other cultures is one of our cultural ideals that isn't too grounded in reality. We share common culture and biology, but still have a lot of cultural traits and traditions that infuriate or disgust each other, and that's not necessarily wrong. To quote the example from our original discussion 8 years back, I don't want to go to war with a civilization that thinks you should deal with overpopulation by killing off anyone who doesn't get on the honor roll as a kid, and a lot of aliens that give birth to litters might have developed that habit and kept to it long before some form of birth control was invented. As such, I don't really want to be good friends with them either, or get to know them, and it's much easier to stay away from conflict by just staying far away. I don't find this case too compelling though, ultimately because the easiest way to enforce this policy would be to loudly broadcast it to everyone as soon as they could hear and comprehend it, and we should be able to hear it now, along with long messages of self-justification from this or that empire proclaiming how awesome they are. Given how closely this mimics the behavior of critters marking territory and trumpeting about themselves, I find this behavior much more believable than silence.
See also Quarantine Hypothesis. Quarantine is self-imposed. Zoo Hypothesis. Inter-universe migration.
A common reason suggested to explain why intelligence and galactic civilizations might be common, but missing, is that they developed the technology to travel to greener pastures and do so, which is plausible enough as a motive, but beyond us having no physical evidence of these greener pastures, we also would need to ask why they didn't leave some sort of presence behind. Would we really abandon Earth, for instance? And would we still not want resources near us? And if the answer was no, the pastures are truly that green and abundant, why not use some of that massive abundance to power a beacon on Earth or nearby, screaming into the void, hey, here's the diagram for how to build new and infinite universes. Have fun, enjoy, share it forward. And by the way, we are attached to our homeworld and bigger than you, so stay away from it since it matters to us, has no value to you, and we have quantities and sorts of weapons you would expect from a civilization with access to untold billions of worlds to draw on. And maybe not all would do that, but that's where non-exclusivity comes in. If these places are so much better to migrate to, then at least some will do beacons telling others how. and the only reason you couldn't migrate there and keep your homeworld or other worlds is if it was one way, which means nobody could send back a message they arrived safely, which means many folks would probably decide not to take that leap of faith and stay in this universe anyway.
See also Ascension, Multiverse and Alternate Reality Aliens, Perpetual Motion Machines, Virtual Reality Utopia. Jovian Vacuum Cleaner.
The Jovian Vacuum Cleaner is a popular rare Earth or rare Sun or solar system filter, as it notes that our planet Jupiter has the effect of sweeping up large amounts of clutter that might otherwise bombard Earth with devastating asteroid strikes. This is often coupled to noting that large gas giants in an inner system would eliminate the ability for planets in the habitable zone, though leaves it open to livable moons of that gas giant. While definitely not a great filter, as many systems all likely possess Jupiter analogs in size and distance, it is a good filter overall. Additionally, the Great Tack Hypothesis, that Jupiter may have formed roughly where the modern asteroid belt is now, migrated into somewhere between Earth and Mars orbit, then migrated back out to beyond the modern belt, is a reminder how easily a large planet, or passing rogue planet or star, could perturb a solar system, wiping out early planets with non-technological life, moving them into regions too hot or cold to survive, or ejecting those planets entirely from a solar system.
See also Filter, Great Filter, Rare Earth, Rare Sun. Kardashev Scale.
The Kardashev Scale is an astronomical approach to civilizations, seeking to discuss them in terms of our ability to see them, but does tend to get used for discussing the size or might of a civilization too, in the sense of a civilization with an entire planet, star, or galaxy's energy available to it. A Kardashev 1 civilization, or K1 Civ, is one that uses so much power that it would significantly alter its planet's spectrum so as to be unmistakable for it to be natural. Kardashev 2 does that to an entire star, such as a Dyson swarm, and Kardashev 3 does this to an entire galaxy. This is the end of the original scale Kardashev proposed, but we consider a supercluster scale or Grabby Alien civilizations to be K4, and K5 to be one that does this to an entire Hubble volume or observable universe. See our Kardashev Scale episode for more discussion of how insanely massive K2 and K3 civilizations can be, and examples of what they would look like.
See also Dyson Dilemma, Grabby Aliens, Loud Aliens. Large Moon Needed.
Our moon is enormous, the largest non-planet of the inner system, and more massive than Pluto and most other dwarf planets. It is the primary source of tides, believed to be a major factor in Earth's axial tilt and thus seasons, is likely connected in part to Earth's tectonics, and is also believed to have caused Earth to slow in rotation, down from a period of roughly 10 hours like the gas giants have. As such, it has often been contemplated as a great filter for the Fermi Paradox, though modeling earlier this century suggested large moons around Earth-like planets might be as common as 5 to 10% of star systems, still making a noteworthy filter, but removing it from its long-held status as one of the more probable major or great filters. This was a model though, and our knowledge of exomoons is still virtually zero, and some newer work has called into question how probable it is for large moons to be around planets in the Goldilocks Zone of most systems, particularly dimmer stars where habitable planets would be experiencing far more gravity from their sun at habitable zone distances. While it would still seem unlikely that a large moon would be a full great filter, it is doubtless a filter and may turn out to be a strong one as was previously believed.
See also Filter, Goldilocks Zone, Great Filter, Rare Earth, Rare Sun, Tectonic Activity Needed. Late Filters.
Late filters are those which are thought to weed out potential loud aliens after they have reached our current state, and generally fall into two categories. Either 1, civilizations in our state tend to kill themselves off before getting into space, or 2, the ability to colonize space is deemed impractical, undesirable, or flat out impossible. As with other filter groups, it can be the case that several are true and filter civilizations to varying and compounding degrees.
See also Asymptotic Burnout, Aurora Effect, Berserkers and Hibernating Monsters, Compounding Filters, Filters, Great Filter, Hermit Shoplifter Hypothesis, Inevitable intelligence implosions, percolation theory, technological singularity, technological time bombs. Life or intelligence is not natural.
This is the general category that suggests all notions of how evolution works don't match up to reality, such as abiogenesis being much more likely than not to never happen anywhere in the universe, or that intelligence could only arise from a supernatural origin, or via us being in a simulation, or the mad dreams of a Boltzmann brain. Generally, this category doesn't tend to be subject to falsifiability scientifically, and thus is hard to discuss in terms of likelihood and flaws. Obviously, if the first life were made by an all-powerful deity or some programmer in a higher reality, it is going to be relevant to the Fermi Paradox, but on the surface we might not be able to tell if they had taken the approach of making the universe calibrated to produce us naturally or not, and we wouldn't know if they did or didn't want other intelligent civilizations in that universe. Nonetheless, while we can't discuss it in depth in a scientific context, it does represent a logical set of solutions to the Fermi Paradox, as the paradox is mostly built around the assumption that life can spontaneously arise anywhere the conditions are right, and that intelligence is a reasonable pathway for evolution. If that is not true, there is no paradox. Though it does raise other problems too, a popular one to be to wonder why the universe is so large if it is artificial and we are all that's in it.
See also Boltzmann Brain, simulation argument. Loud aliens.
Loud aliens represent the default problem of the Fermi Paradox and the Great Silence, as they are what we expect to see if space colonization is practical. Loud aliens are distinguished by possessing all three of these characteristics. They expand into a galaxy fast, they last a long time, and they make visible changes to those areas they reach. They may or may not expand beyond their own galaxy or skip primitive or undesirable planets. They may or may not be biological anymore, or be some AI successor that wiped their precursors out. They may be unified in goal and direction, or entirely divergent and unconnected to branches of their original civilization back on their homeworld. But the key characteristic that distinguishes them from other types of civilizations is that they essentially leave a very detectable presence by being big, visible, and long-lasting. We call that loud since the usual context for discussions in the 1970s and 80s, when most of this was first getting seriously discussed, revolved around SETI listening for radio communications and signals. Glaringly obvious aliens is perhaps a more appropriate term, and they are the low-hanging fruit of the Fermi Paradox, and their apparent absence is one of the main reasons for the Fermi Paradox. By default, that's what we think we should expect to see in a universe as old and as large as this one, ancient, giant, and very visible civilizations, because it's what we want to do, go out and explore and colonize new worlds and put up big beacons and billboards advertising them for visits and immigration, and just keep on doing that in an ever-expanding wave until the stars themselves burn out. It is the opposite approach to hidden civilizations, as the assumed strength correlates to sheer numbers and resources, or that hiding is not practical.
See also Dyson Dilemma, Grabby Aliens, Great Silence, Quiet Aliens, SETI, They Hide from Everyone. Low-energy ecosystems.
Low-energy ecosystems, or low-energy flux ecosystems, would be those in which a vast abundant supply of energy like photosynthesis was not available. In its absence, a given planet or moon simply doesn't have that much biomass available to make its ecosystem. A small asteroid with life on it, even with plentiful sunlight, is going to have a hard time having an ecosystem big enough for the sorts of complex evolution and diversity Earth has too. A subsurface ocean on a large moon has this same problem, and an icy world far from the sun might have lots of slow-moving life that lived many centuries, but might not have had many overall generations to evolve yet. We have to be mindful of this when contemplating potential life-bearing worlds outside the Goldilocks zone of a system, because they might have life, but probably couldn't have had time and scale enough to have permitted intelligence to arise as it did on Earth. That said, you might have some world where natural ambient temperature superconductors formed it organically, so the big human-scale brain was so compact and low energy that it fit on a thumbnail and ran on less power than a tiny LED light of the type we use to indicate power is on for a device or its status, in which case intelligence might come very quickly as it's very cheap and compact. See our episode Non-Carbon-Based Life for further discussion, but this concept of low-energy ecosystems is generally viewed as a strong filter on what sort of places life can arise on and how long it would take. so that a frozen planet might have intelligent life, but not till the year 1 trillion AD.
See also Goldilocks Zone. Mediocrity Principle.
The Mediocrity Principle, or Copernican Principle, is a foundational concept of science and one of the two principal ways we look at the universe, and evidence when details are few and hard to come by. This approach assumes anything we encounter is most probably a fairly normal and mediocre example of whatever type of thing it was. As we gather more examples, we can increase our degree of certainty that something was normal, or realize that it was not, and our encounter with it was freak luck. This is our default approach to science, and in the context of the Fermi Paradox is why we assume any paradox is in play, as the Copernican Principle specifically reasons that Earth is not special, not the center of the universe, and likely a mediocre example of planets all in all. This reasoning is also embedded into Drake's equation, which is essentially trying to determine how improbable and non-mediocre Earth is, and in the idea of non-exclusivity, which takes that as the default view of any given condition or alien behavior. Its partner, the Anthropic Principle, takes a different view, but critically, both exist principally for contemplation in ignorance, where gathering more data is difficult.
See also Anthropic Principle, Drake's Equation, Non-Exclusivity. Metallicity.
The metallicity of a star is defined as the percentage of its mass that is not hydrogen and helium, and thus the first stars would have been about 1 part per billion metallicity, and that's just lithium-6 and 7. These are the hypothetical population 3 stars, with population 2 being middle-aged low metallicity stars, and population 1 being the newer ones like our own Sun. As stars aged and died, we saw a rise in such elements scattered throughout the universe. As time went on, the amount of metals built up overall, and the planets a star has will have formed from the same nebula it did, so a star with a higher metallicity should have more rocky material. Thus there are more metals and more plausible planets for life as time goes on. This is not evenly spread through, and even relatively early on in the universe you would have had planets form and hydrogen and helium blown away by solar wind. So a Saturn-mass planet that only had 1% metallicity can still leave an Earth-mass rock behind if you strip that hydrogen and helium off. So too, several local supernovae could have produced a high pocket of metals fairly early on in the universe, and they do tend to happen in clusters like that. Thus, this is more of a hypothetical timer affecting the timeline and probability of a metal-rich world forming in quantity in places where life might plausibly develop and not be wiped out quickly, like near a galactic core or in an ultra-dense globular cluster.
See also carbon and nitrogen ratios, critical element scarcity, galaxy type and stability, rare sun, stellar neighborhood. Miniaturization.
A common suggestion, especially in post-biological civilization context, is that humanity would never go to the stars because we keep finding ways to get ever more efficient or miniaturized with our computers. This has the issue of non-exclusivity unless we're assuming post-biologicals wipe out everyone else. But it is worth noting that smaller and faster civilizations would likely find interstellar travel time lag even more upsetting, as they might be experiencing a subjective time rate far faster than we do, making multi-century journeys feel like eons. Of course, instant travel by light transmission alleviates that problem by letting you build a robot who travels to a star and builds a receiver. We discussed this in more detail in our episode, The Fermi Paradox, Digital Empires and Miniaturization, which examines concepts like Kardashev 2 digital civilizations and Matryoshka brains. But at its core, while they may build an expanding central hub, even to the Birch planet scale, which I'll just name a Birch brain at this point, they have every reason to engage in resource hoarding and sending out automated missions to do that. So no matter how efficient they get, when a single automated probe can be dispatched to replicate and bring back more raw materials and fuel, they still have every reason to send it. Being 99.99% efficient just means you can do 100 times more with the same entropy as someone who is 99% efficient, so adding to the base supply still helps.
See also Kardashev Scale, Non-Exclusivity, Post-Biological. Multiverse and Alternate Reality Aliens.
Our universe is huge, and likely expands far beyond the observable portion and the cosmological event horizon, but it may be a tiny spot in comparison to all reality in the multiverse. As such, if travel is possible between here and that wider realm, We must not only consider how migration to it might appear compared to interstellar migration, but if we might get visitors from such multiverses. As an example, any given multiverse that develops travel should travel to more than one of its cousins, meaning a lot of visitations. Also, if it is easier to step from here to one of the many copies of Earth where humanity never evolved or died off early, that is vastly easier colonization than interstellar travel. And worse, there would be far more uninhabited Earth clones than planets in our observable universe, and probably a far higher ratio than 1 in a quadrillion of such worlds to one where humanity or some other intelligence emerged. So this is a case that is both a decent Fermi Paradox solution, if reality is set up this way, as well as one that might only exacerbate the Fermi Paradox if true, as we would need to worry about visitors or invaders from other realities, not just other stars. See our episodes Fermi Paradox Multiverse and Multiverse Warfare for more discussion.
See also Great Silence, Inter-Universe Migration, Perpetual Motion Machines, Multiverse and Alternate Reality Aliens. Solution exacerbates the Fermi Paradox, Time Travel. Neurohacking for Happiness.
Similar to virtual utopia, this idea contemplates that humanity might prefer artificial worlds or mind states to colonize the galaxy. However, it assumes a specific approach of us putting wires into our head that stimulate our pleasure centers. This has a non-exclusivity element of many people potentially finding that undesirable to try, but we can contemplate involuntary options, like a tyranny using it to keep people in line. However, such a civilization ought to have a desire to expand its resources, even if just by mining them elsewhere and bringing them in. It is possible they would not have great and reliable automation the way a virtual utopia essentially has to have, but unlikely. This is a technology that is likely very possible, and sooner than not, tackling it might be a late filter. At the same time, we also have other sensations, like stimulating satisfaction or sadness or preventing boredom, that can shift the dynamic we would expect to happen away from the implication of billions of people sitting in a cheerful, drooling stupor. Also, there is no implication that technology would leave you in a state of stupor. I can see many different ways this could turn out, and thus for that reason can't see it being a Fermi Paradox solution, merely a decent later filter, as there is no obvious and convergent ending for such tech and civilization with it. One more interesting scenario, though, would be our hermit shoplifter hypothesis, in tandem with this being a vulnerable world scenario, as people might flee with this technology to deep intergalactic space to enjoy it on their own for eons by themselves, where no one can unhook them, while those who avoid the tech or use it to control others might find themselves self-imposing a quarantine, not letting anyone expand outside their grip until eventually the place collapses.
See also Hermit Shoplifter Hypothesis, Self-Imposed Quarantine, Virtual Reality Utopia. Nihilism or ennui.
One of the more common concerns for civilizations is that they may come to a state of nihilism or ennui where they simply feel they have no purpose or collapse. While normally this would seem at odds with non-exclusivity, as we would not expect every person in a civilization, let alone every civilization, to suddenly feel their existence had no purpose, this Fermi Paradox solution argues that this is an inevitable state of all civilizations, something they must converge to, that existence has no meaning or purpose, and thus it is inevitable that civilizations that are constantly growing more intelligent and knowledgeable will come to this conclusion. It is also often suggested as a fate for non-biologicals, such as a computer mind that will leap into sentience and begin building its brain bigger and bigger until it becomes so smart it can't escape the realization its existence does not matter, too clever to fall for self-deceptions, and that continuing doesn't serve any purpose and shuts itself off. If it began by wiping out all the biological life around it, Skynet style, this would become a convergent solution for the Fermi Paradox, since we tend to assume everyone invents computers, and this would be an example of a technological time bomb, whereas a civilization simply drifting into a feeling of pointlessness would fall more into the category of a psychic poison. While a popular solution, or rather a popular category of solutions, this has a few big flaws. First, it is assuming life genuinely does not have a meaning or purpose, which for my part I don't believe, but regardless, is not something proven one way or another, and honestly not something we would expect science to ever usefully answer, so it would be hard to imagine it convincing an entire civilization without exception. Though there is an assumption they may have grown vastly more intelligent and self-honest, albeit this itself is at odds with other Fermi Paradox solutions that assume intelligence and technology create an environment where de-evolution occurs and intelligence diminishes over time, as we see in the film Idiocracy and explored in our episode Human De-Evolution, Morlocks and Chuds. Second, it is assuming that a feeling of lacking purpose in an ultimate existential sense would cause inevitable mass suicide, and that is clearly not true for humans, as while that can definitely lead to depression, there are a lot of people who function for decades while depressed, and also lots of nihilists I know who do seem to operate just fine. To be fair, this could be an example of cognitive dissonance, and while we assume ultra-smart people or logical machines would be immune to this, I have my doubts. We'll explore them more in next month's episode, Nihilistic Aliens. And third, even if all that were true, it still doesn't mean it would get everyone, since there are lots of people who presumably actively avoid thinking about it, and if necessary convince themselves and the remainder of their civilization that even contemplating that type of question was inherently dangerous. Something I think many of us already at least partially believe anyway. If half your civilization falls into despair, then the other half, probably being aware of why, has every reason to begin taking preventative action, even including active dishonesty to themselves and their citizens, or including indoctrination tactics or outright brainwashing against believing it. Though again, the idea is that folks might eventually get too smart to fall for it, even for a moment, and that is always an option. For all those reasons, I tend to feel this is not a strong solution for the Fermi Paradox, but it is one of the more disturbing solutions because it does feel like it has some merit.
See also non-exclusivity, psychic poison, technological singularity, technological time bombs. Non-exclusivity.
Non-exclusivity is not a Fermi Paradox solution, but rather the minefield that most proposed solutions die in. It is very common for a solution to assume some behavior or capability that is universal. In practice, we cannot assume very many things are. For instance, the space race was conducted between the mostly communist Soviet Union and the mostly capitalist United States, and both groups got significant victories in that race, so we have no reason to believe that space travel is exclusive to capitalist or communist economic systems. We may find one tends to be more common or successful, or that both are rarities, but space travel and settlement would seem to be non-exclusive to economic systems, and many other traits would also be non-exclusive. Whether they played baseball or football, whether they were red-haired or blonde or bald, had hands or tentacles, believed in Santa Claus or not, would all seem factors that had little to no impact on their ability to make spaceships. Now, some things probably do have exclusivity. For instance, we can assume building spaceships is exclusive to civilizations with a knowledge of basic math and physics. We can imagine exceptions, but exclusivity need not be 100%. It just needs to be so high as to count as a strong filter. We assume a lot of planets are covered in water and may hold intelligent life like dolphins, but be incapable of fire and thus cannot invent technology. Some may eventually, but if only 1 in 1,000 submarine civilizations get to space, and we only get one intelligent civilization arising per galaxy, then these would still be so rare as not to present a problem for the Fermi Paradox. It would also mean there were millions of these star-faring dolphin species in the observable universe, as a reminder that the universe is way bigger than our galaxy is. Non-exclusivity is one of the most important tools for examining the paradox, and is a tricky one at times, because people often have a preferred solution that matches up to their own ideology, and so it is easy to believe that solution and that all alien civilizations converge to that belief. Which may well be true too. We couldn't really say for sure until we have scattered interstellar colonies that hold disparate views from each other on said issue, though for my own part I tend to assume many systems can be made to work, if not all as well, and that high-tech post-scarcity civilizations can make a lot of systems work by sheer abundance and brute force, and that space colonization will often be most attractive to those who want a clean canvas to set societies up on. If you've got a minority religious or political view, jumping on starships with a bunch of your allies for a new world has its appeal, and a lot of people back home might cheerfully fund the endeavor to send your most fanatical followers away and just assume your colony will collapse or change views with time, strangled by its own smug ideals. Still, this is the main rebuttal to challenges to a proposed solution as violating non-exclusivity, that the behavior or trait in question may not be universal, but that it is so strongly convergent that very nearly every civilization capable of space travel will get this behavior or trait before getting to the interstellar scale, or that only civilizations with this trait or behavior last long, thus maybe only half have it when they began, but after a millennia, 99% who didn't go extinct, and if the average interstellar civilization lasted a million years, then 99.999% of civilizations currently around would have that behavior or trait. Needless to say, the arguments for convergence should be very strong ones, as should those for why a given semi-exclusive trait need not be, like building an interstellar spaceship when you can't figure out basic math. And even strongly logical reasons need to be questioned. After all, if someone were to prove conclusively that free will and purpose didn't exist, causing many logical people to give up on life, you would still have lots of logical folks who did not, and lots of folks who refuse to even discuss the option or review that evidence. So too, computers would seem a no-brainer for space travel, but advanced ones beyond what we currently have, or even had in the 1990s, are not necessary for navigating space, even interstellar space, so a civilization very worried about AI could ban advanced computing and probably still colonize space. That one exception might be the only surviving civilization of thousands that arose in their galaxy, and yet they could settle the whole place, including the burned out or grey-gooed planets where AI ran amok and wiped everyone out. On the other hand, just because it is possible for some space whale species to evolve in an asteroid belt and naturally adapt for interstellar travel, does not mean this occurs often enough to really circumvent the exclusive relationship of developing space travel and a knowledge of science. Of course, that probably deserves the caveat of keeping in mind that what's normal probably isn't what's right for the Fermi Paradox. If 99% of species wipe themselves out within a century of inventing weapons of mass destruction, that 1% remaining is still sufficient to colonize the galaxy it is inside, and even its neighboring galaxies, colonized by the lucky freaks who didn't succumb to normal odds. Normal for spacefaring civilizations is generally what we ultimately mean. After all, what seems normal for life on most planets at the moment is that it does not exist, is dead, or is very stunted and minimal.
See also nihilism or ennui, technological singularity. Ocean to land ratio.
Water is one of the most common molecules in the universe, and so common that most of this planet is covered in it, at an average of a few miles deep. If Earth had half as much water or double, it would look very, very different, and Earth is constantly losing hydrogen, 2/3 of the atoms in water to atmospheric stripping. Most planets would begin with a great deal more hydrogen than Earth currently has, and lose it based on many factors, but principally their sun's spectrum and intensity at their planet, and that planet's own gravity or escape velocity. We believe Earth, left to its own devices, will be a dead desert planet in roughly another billion years, long before the sun becomes a red giant. The universe may be full of fossilized worlds covered in sand dunes where the clock ran out as their sun heated up their world and stole its seas and sky. If Earth were bigger, then we would likely have more hydrogen than now, and principally as water, making us an ocean planet. If we were less massive or closer to our sun, or its spectrum harsher, we might have lost all our seas and sky before ever the first animal evolved out of the ocean to live on land. This may mean very few planets have a window where there's a lot of dry land for life to develop fire and technology on during the time intelligent life exists. We may be an extreme rarity of having developed land life and technology while land existed to do it on. Though alternatively, we have found a lot of water is in our planetary mantle, and depth of sea and pressure at the ocean bottom likely plays a role in how much is shoved into the mantle, so there may be self-regulating cycles in play that favor conditions allowing a good mix of sea and land. See our episodes Ocean Planets and Hycean Worlds for more discussion of the implications of more water.
See also filter, rare Earth, rare Sun. Orbital eccentricity.
While we always picture orbits as circles, in truth they are all elliptical, and how stretched they are is the eccentricity of that ellipse or orbit, where a circle has 0 eccentricity and one stretched to be a nearly flat line has an eccentricity of 1. The more eccentric an orbit, the more its sunlight varies over the year, as a planet further from the sun gets less. This is not the cause of seasons, that's axial tilt, but Earth is closest to the sun in January and furthest in July, about 2 weeks after each solstice, and backwards of what folks in the northern hemisphere would tend to expect. A planet twice as far from the Sun gets a quarter of the light, so a high eccentricity planet would have the equivalent of a season from its eccentricity in a case like that, and may be rendered uninhabitable by too much eccentricity, especially as planets spend more of their time on their outer track than when closer to their star, and bigger stars would have more distant habitable zones with longer orbital periods, which might make a winter a year long if done this way. Alternatively, a red dwarf may have seasonal variation, even on a tidally locked planet via eccentricity. However, while Earth has low eccentricity, it is not impressively low. Both Neptune and Venus have more circular orbits around the Sun, so we conclude that eccentricity is at most a minor filter of the Fermi Paradox, though would contribute to a wider rare Earth great filter.
See also Axial Tilt, Filter, Great Filter, Rare Earth. Our galaxy isn't the whole universe.
One of the most common oversights in discussion of the Fermi Paradox is to treat our galaxy like it is an island unreachable for others, and to ignore that if the observable universe were compared to our planet in size, our own galaxy would be about the size of a house on that planet, and that galaxies tend to be spaced out much like houses. Some share walls or are separated by strips of land no wider than that house. Others are surrounded by several times their dimension in undeveloped land. But for comparison, there is probably only about 1 trillion cubic AU of space in habitable zones of stars in this galaxy, while there's many trillions of times more space that isn't in a habitable zone, even under optimistic models in this galaxy. So thinking of traveling between galaxies is not contemplating the same sort of jump in scale that traveling between stars or even planets is. Also, there's lots of random stars in between most galaxies that can serve as waypoints, and a civilization that developed 1 billion years ago when our universe was just under 13 billion years old, not just shy of 14 as now, and could only travel at 10% of light speed, would still have plausibly colonized 100 million light years of space all around them by now. So we cannot assume some freak occurrence in this galaxy is the answer to the Fermi Paradox, since if life was wiped out here 4 billion years ago, and Earth was just the first of many to recently develop intelligence again, that would not explain why someone from another galaxy hadn't settled this galaxy in the meantime. We also cannot ignore that advanced civilizations on the Kardashev Scale who colonized their whole galaxy are likely to qualify as loud aliens, and to such a degree as to be visible to us even when hundreds of millions of light years away, such as contemplated in the Dyson Dilemma. This is also only exacerbated by FTL, faster than light travel, since it not only means people could jump galaxies easier, but introduces areas outside our observable universe into play. That universe beyond the cosmological event horizon may be infinite, we do not know, but we are confident it is likely many times bigger than our observable region, possibly many trillions of times, and could have sent colony fleets into our region by now too via FTL.
See also Dyson Dilemma, FTL, Faster Than Light Travel, Kardashev Scale, Loud Aliens, Solution Exacerbates the Fermi Paradox. Oxygen Content.
Oxygen is a weird substance. It reacts with nearly everything and is a core element of water, one of the most abundant molecules in the universe and the de facto king of solvents for solutions life might arise in, though we have contemplated other options like ammonia in its own episode. As such, oxygen is very necessary to known biochemistry, and free oxygen is critical to modern biological life, but it was once a poison emitted as a waste product of early life. Oxygen is hyperabundant throughout the cosmos, as the third most common element, distantly behind hydrogen and helium, and makes up the largest portion of atoms on most terrestrial planets and moons. And while poisonous, it was very easy for it to be absorbed into local rocks. But as life grew more abundant and active, it overwhelmed the ability of local geology to churn around and expose more materials to reabsorb emitted oxygen, allowing the concentration to slowly build up. This was a slow event and allowed many organisms to not only adapt to it, but thrive by using oxygen to breathe, as you and I and every animal now does, inhaling O2 and exhaling CO2, carbon dioxide. Higher concentrations can be handy for allowing mobile, breathing life, but too high a concentration might expose a planet to constant forest fires. Planets with slower or faster tectonics might either allow such an atmospheric saturation of oxygen to happen too quickly for life to adapt to, killing all life off, or be so quick to churn that no significant amount of free oxygen ever develops for animals to breathe. This may be an issue with terraforming many planets that require brute force techniques to keep sufficient oxygen in the air. Free oxygen is also one of our strongest candidates for an astronomically visible biosignature on exoplanets, as we have few other suspected natural causes for free oxygen to be abundant besides a presence of life.
See also rare earth tectonic activity. Panspermia.
We do not yet know how life began on Earth, and while deep-sea thermal vents and tidal pools have been popular candidates, another scientific theory for the origin of life is that it may have germinated on comets and been spread to Earth and perhaps other worlds when those impacted Earth and, we believe, brought the water that made our oceans. Should we find life on Mars or Venus or Europa that shared any basic DNA with terrestrial life, it would indicate this method of panspermia had either occurred or a parallel process had occurred that had moved life from the planet it began on to the others. But there are many other types of panspermia that might occur, including interstellar options that might permeate an entire galaxy over time, as we explored in space whales and bioships. Indeed, some argue that life evolving to become spacefaring, naturally or artificially, and colonizing a galaxy in the process, is the inevitable purpose of life, and similar notions would apply to civilizations that created new universes and spread light to them or to dead universes. However, while it is a common concept to be raised in regard to the Fermi Paradox, it is not a solution and indeed might exacerbate the problem, since it would imply interplanetary or even interstellar colonization by simple organisms is probable, and thus spacefaring technological civilizations surely could. And given our fossil record, it is abundantly clear that at most, the very simplest early steps of life occurred off Earth, with the rest being on this planet and subject to any other rare Earth filters that would apply to life which had originated in a tidal pool or deep-sea vent locally.
See also filter, percolation theory, rare earth, rare intelligence. Percolation theory.
Percolation theory is an approach to the Fermi Paradox via mathematical modeling to where we assume the initial point of colonization sends out colony ships to colonies that eventually might send out their own. First done by Jeffrey Landis in the early 90s, this has become a common basic model for galactic colonization, and posits that once these colonies are established, they basically act independently as disconnected nodes with only loose ties to neighbors, that you can only send a colony ship so far, and that many colonies will be long sending out their own colonies and may never do so, or may fail to successfully establish themselves, something examined more in the newer concept, the Aurora Effect. I would generally view both as an attempt to rebut the Hart-Tipler Conjecture. While this is an essentially logical model, much like Drake's equation, it has some potential conceptual flaws. First, it is assuming slow interstellar travel, not just slower than light speed, but typically 1% light speed or less, what we call colonizing. I have no objection to lack of FTL, but the model does not really serve much purpose once we get to more relativistic speeds and don't assume colonists are being ultra picky about what stars they settle. Ships do not need fuel to keep moving, so have no limit on their range besides patience and internal life support energy and supplies, and the very existence of any generation ship requires technology that makes settling any star system viable, not just Earth-Sun analogs. In that context, if we are assuming colony ships moving 5 to 10% of light speed, or higher, and settling any system they come across, not taking several centuries to get to the nearest Earth-Sun analog, it's not really a matter of percolation, just more like a wave rippling out from the homeworld. Any local impedance just doesn't matter much in the waves reaching the shores of that pond. We also should not assume the next viable system for colonization is typically being reached by the nearest developed colony. Odds are good Earth will still be sending out colony fleets long after it's seeded the nearest 1,000 or so systems, since that's only a region about 30 light years around Earth, and that each is likely to grow exponentially towards being a Dyson swarm or Kardashev 2 civilization, and probably only needs a few thousand years to get there, at which point it would be able to send a robust colonial fleet to every single star system in their region of the galaxy without denting their resources beyond making a minor footnote in their system budget. In scenarios like this, there is no reason not to assume colonization isn't generally moving out at nearly the speed their ships can travel and not needing to much consider leapfrogging because there's always more developed systems a little further behind sending out colony ships, not the nearest neighboring colonized system. That's a very different picture than when we look at the same volume of 30 light years and say there's only about 20 yellow suns in that region and assume maybe 10% of them have a planet worth trying to settle and terraform, and so maybe 2 or 3 would get colonized and thousands of years later might have grown to the point of considering sending a colony ship of their own to 2 or 3 viable candidates near them. It also doesn't assume options like seed ships, automated vessels that do virtually all the colonial work ahead of your arrival, or Gardener ships, which are ships or fleets that just stop at a system, unload about half their crew and passengers while loading up on fuel and raw materials, then head off to the next location, breeding up to full strength during the trip and building colonial gear during the process. In the 20th century, humanity doubled its population twice, so it would be very easy to believe a high-tech civilization with options like life extension technology and advanced automation might have no problem zigzagging their way out to the galactic rim, colonizing a system at every stop, occasionally building an extra ship for their colonial fleet and dividing that fleet every so often to branch their way out to the edge of the galaxy and beyond. As we examined in our Life in a Space Colony series and our Generation Ships series. Again, there's nothing wrong with percolation theory in of itself, but it's presupposing each new colony only has a few candidates for future settlement in reach and cannot draw on their homeworld for any help. This can be partially true if we never make anything better than the Ryan drive work, and more a conservative assumption of its speed at that, but it's still assuming too sharp a cutoff on what systems people would settle and develop. One caveat though, this approach still works in some of our more high-speed colony options, as we have discussed hurling colonial fleets out of our system by enormous pushing lasers and aiming them towards black holes a large way across the galaxy, where they can change direction and slow, or into enormous red giants, where they can burn speed off, passing through their very thin upper atmospheres. So whereas a fusion-powered ship might be limited 10% of light speed and cause a colonization wave out at perhaps 5% of light speed, or slower, some pushing beam-driven system might leave our system at half of light speed. They could then arrive at a region of the galaxy 10,000 light-years away in 20,000 years, where a normal colonization at 5% might reach it in 200,000 years. In this way, large and uncommon red giants, or rare black holes, become ultra-valuable galactic real estate from which new spheres of colonization would emerge, in a fashion more akin to the model of percolation theory. This can also apply to intergalactic colonization.
See also Aurora Effect, Dyson Dilemma, Drake's Equation, Hart-Tipler Conjecture. Perpetual motion machines.
Perpetual motion machines are an example of a technology that tends to throw chaos into future predictions, as it's a technology that disrupts a lot of our normal limitations on space settlement as well as our motivations for doing development. For instance, a civilization with an infinite and compact source of energy does not need to spend time building Dyson swarms or worrying about resource hoarding in the face of inevitable entropy. Typically, such empowering technologies only exacerbate the Fermi Paradox, since they make colonization so much easier and faster, but in this case, the technology just has so many hard-to-predict side effects to permit that as a solid conclusion. For instance, a civilization with such a power source might decide its best pathway for long-term survival is to make sure no alien menace can reach it, and as we often joke on this show, if you explore interstellar space and don't find any alien civilizations, just wait a bit, because your own scattered and divergent colonies will effectively become alien, and as such a threat, where one wouldn't have existed before, and which you do not need since you have an unlimited energy supply, which can be used to produce new matter too. Alternatively, far distant alien civilizations have no reason to bother with you or vice versa, as you have nothing they need and represent no menace a proximate sibling might, such as one that felt it had a claim on cultural or religious relics or territories. Or alternatively, that power supply might function by opening a portal to a younger and more energetic universe that you might be preferring to migrate to, or get invaded from. It's not that these options are particularly likely, it's that the technology introduces too many unpredictable effects for us to make reliable predictions about how they would behave or what they would look like. As another example, we often say there's an absence of Kardashev 3 civilizations out in the wider universe because we'd expect far more infrared waste heat in a galaxy they control than any we see, but a perpetual motion machine is the sort of technology that would not reliably leave that sort of signature, and of course utterly violates the known laws of physics.
See also solution exacerbates the Fermi Paradox. Post-biological.
Post-biological is a catch-all term for any advanced life form whose overall physiology or psychology is more artificial or engineered than natural, such as we would expect from artificial intelligence, androids, uplifted organisms, cyborgs, late-stage transhumans, or more metaphysical ascended or transcended entities. There is a tendency to assume spacefaring civilizations are more than likely populated by these. Its principal relevance to the Fermi Paradox is that our default assumption under the Hart-Tipler Conjecture is that spacefaring civilizations tend to have the same motivations we expect from anything produced by Darwinian evolution or early civilization. Which is to say, we assume an AI that wipes us out will be intelligent and aggressive and growth-oriented, as that's what evolution tends to favor. But post-biological life might suppress or remove or re-engineer their minds and biologies to alter these paradigms and become less predictable in that regard. It also alters what sort of megastructures they might build, as a computer mind might mostly want power collectors and computer chips, not simulated gravity cylinder habitats and terraformed planets, and may be more interested in ultra-low-risk personal survival strategies based around billion-year timelines or longer, not our own centennial approach. Nonetheless, many strategies would be expected to still conform to the idea of survival of the individual or greater whole, and utilize logic for determining the right action and course.
See also Hart-Tipler Conjecture. Prime Directive.
This solution derives from the prime directive of Starfleet in Star Trek, that no primitive civilization is to be interfered with, and has some clear roots in our own rather checkered colonial era on Earth. In that regard, it is not too hard to imagine civilizations older and wiser than us choosing to leave us alone, though at this point that would tend to require fairly actively tinkering to hide themselves from us too, which is arguably still interference since you're tampering with core scientific evidence they can gather about the state of the universe around them. In any event, this is one of the most hotly debated topics of extraterrestrial speculation, and we have done entire episodes on it. Both Smug Aliens and Fermi Paradox Prime Directive take a look at some of the flaws, strengths, reasons, and challenges of this approach in detail. It suffers strongly from non-exclusivity though, as you must explain how and why you were able to maintain a quarantine around a planet for millions of years with any hope of success, in the face of changing perspective of your own civilization, resource budgets of folks objecting to maintaining an unending quarantine, members of your civilization that will gladly trade their lives to save primitives from a plague or asteroid, and rival empires who might not agree and dare you to fire on their ships. We rarely see the Klingons, Ferengi, or Romulans flying to primitive worlds near the Federation and just landing on them, because unless Starfleet was willing to shoot at them every time, it would tend to show how enforceable this policy is in the long term, or rather, how unenforceable it is.
See also Interdiction Hypothesis, Quarantine Hypothesis, Zoo Hypothesis. Psychic Poison.
Psychic poison is a broad class of hypothesis for how civilizations might destroy themselves in more existential ways than a nuclear war or unleashing a homicidal superintelligent computer mind. Some common examples suggested would be a planet that came to believe that free will was an illusion, or ceased to believe there was any purpose to existence or reason to strive toward goals. Or more literally, some very intense narcotic that is intensely pleasurable or relaxing, but leaves its users in no fit state to pursue goals like space colonization or long-term stable civilizations. Other options can include adopting a given political or economic system that someone feels inevitably leads to ruin. These are often fairly subjective, and many do run into difficulties with non-exclusivity, as there is no reason to assume everyone on a given planet does this, let alone universally across unconnected galaxies with species that might have very different social and neurological architectures. Nonetheless, it is one of the more popular and populated categories of Fermi Paradox solutions, and many of the other solutions today could be viewed as examples of these sorts of psychic poisons or overlap into them. These differ from technological time bombs in that these are assumed to be more psychological or sociological, but they may overlap.
See also Non-Exclusivity Technological Time Bomb. Quarantine Hypothesis.
Quarantine hypothesis is a subset or cousin of zoo hypothesis that assumes Earth is viewed as dangerous in some fashion, and thus has to be quarantined from contact. This has the same problem zoo hypothesis has of asking why anyone would go to such an elaborate effort to keep us in the dark, but also, since it implies danger, asking why they don't simply wipe us out, or alter us. And indeed they might have, since one approach post-biological spacefaring civilizations might use is to send in a lot of nanobots to quietly dig into our brains, copy them, upload our minds to some virtual reality, kill our physical bodies, and keep that virtual world running on some mega computer built out of our planet or some fortified asteroid inside their own core worlds. There are many proposed reasons for such quarantines. Us being violent by nature is one, especially as it leaves an obvious implied reason why they wouldn't stoop to killing us off. But folks have suggested many others over the years, and it's popular in sci-fi. Such a quarantine might be temporary too, merely until we reach a certain stage of development, until which time we're under Prime Directive-style non-interference quarantine, and there may be fleets surrounding our system waiting to blow up invaders. One issue with this, though, is the implication you are trying to maintain a quarantine for potentially millions of years because you found some smart monkeys on some planet, which seems impractical to the point of impossibility, something we explored more in our episode Smug Aliens.
See also Prime Directive, Quarantine is Self-Imposed, Zoo Hypothesis. Quarantine is self-imposed.
Quarantine is self-imposed is a variation of quarantine where a world knowingly prevents travel away from their homeworld, or sometimes are ignorant of it but their government knows, such as if we had secret UFO technology, as many believe. This may be because their totalitarian dictators are afraid of rebels on distant worlds, or fear they might breed enemies by settling interstellar space with divergent cousins, or because they fear we might bring home some ruin by poking our noses out in the deep dark of interstellar space or on some ancient and dangerous world. They may also have been told by some greater empire to keep to their homeworld or they'd lose protection or invite retribution.
See also Prime Directive, Quarantine Hypothesis, Zoo Hypothesis. Quiet Aliens.
Quiet aliens are those who contribute to the Great Silence, the observed condition of the universe by modern astronomy and SETI. Quiet aliens are, by definition, the only kind we currently observe, since they preserve the Fermi Paradox, and loud aliens are what we are looking for with SETI. This essentially is the default state of most aliens discussed as solutions to the Fermi Paradox, and covers everything from those who hide or never colonize space to those who flee to other realities or go extinct quickly.
See also Great Silence, Loud Aliens, SETI. Rare Earth Hypothesis.
Rare Earth probably represents the largest single area of discussion of the Fermi Paradox, as it loosely includes the subcategories of rare sun, rare solar system, rare galaxy, rare complexity, rare intelligence, and rare technology. It also represents our primary great filter, as it is generally thought to include many lesser filters which compound together, everything from how likely life is to originate as simple primordial cells to develop a brain, and every step in between, in addition to factors like geology, gravity, atmosphere makeup, and density, which has changed over Earth's history drastically, ocean to surface ratios, geological events, the size of our moon, the characteristics of our sun, the importance of asteroids or Jupiter-like planets, planetary orbital eccentricity, and many, many more. For the purpose of today's video, we are treating rare Earth as mostly meaning Earth's own traits and the path of life from abiogenesis to basic brains, while giving other subcategories separate treatment. More broadly, it is every filter except the late filters.
See also carbon and nitrogen ratios, compounding filter, critical element scarcity, filter, great filter, ocean to land ratio, rare intelligence, rare sun, rare technology, tectonic activity. Rare intelligence.
Rare intelligence is a general category of Fermi Paradox solutions that assumes intelligence is uncommon in the universe. And while this technically includes both rare Earth solutions and rare technology solutions, we generally mean that life is common enough, but large brains are rare to evolve. This might include the development of complex brains of any significant size, and as we detailed in our episode Rare Intelligence, there are a number of evolutionary barriers to intelligence, along with circumstances which make larger brains a hindrance. While we have a tendency to assume high intelligence is the greatest survival trait, and an inevitable end road for evolution, this is not indicated under our current understanding of evolutionary biology. So it may be that intelligence is a relative anomaly in a wider universe full of alien life, but not much thought.
See also filter, rare earth, rare sun, rare technology. Rare sun.
Rare Sun or rare solar system includes a large variety of possible filters, varying from if a star is stable in its output, such as we looked at in our episode Fermi Paradox solar flares, to if the star lives long enough for life to evolve, or is so dim that only planets close enough to be tidally locked might be warm enough for life. This is probably not a strong candidate for a great filter, as while our Sun seems more stable than most, it doesn't seem to have any particular traits that are very uncommon. Nonetheless, this area includes many probable filters. Stellar spectrum helps determine if a star is likely to rip off atmospheres from their planets, and the brightness of stars increases over time, moving once cold planets into the habitable zone while pushing other once habitable planets into becoming desert wastelands that eventually would lose all seas and atmospheres. Smaller, dimmer systems may have habitable zones too cluttered with debris to form stable planets. Bigger gas giants might migrate and perturb planetary orbits. Binary systems may have few options for long-term stable habitable planets, and so on. While a technological civilization should be able to make homes around nearly any type of star, it is quite likely that stars introduce many harsh conditions to life.
See also filter, Goldilocks Zone, Great Filter. Rare technology.
Rare technology is the filter that suggests intelligence might be decently common, but that technology is less so. And in this context, it is worth remembering that there are many intelligent animals on Earth, but technology of any simple type is rare. Not totally absent, chimps use sticks for instance, but it is notable that we think humans invented such simple tools and discovered fire a million years ago or more. It's only been the last 10,000 years we got pottery and metalworking, which means for 99% of the time we had fire, we didn't use it for making metal or ceramics. So too, some plants wouldn't be very fire-friendly, such as places that rained like crazy or were covered in water and bogs, or had such high oxygen content that fires were very brief and dangerous. We discuss these options more in our Rare Technology episode.
See also Rare Earth, Rare Intelligence. Recent galactic catastrophe or war.
A common suggestion for why life might be common, but not spread all over every star yet, is that it has only recently germinated in these spacefaring races, and two popular reasons why are that there was either a big catastrophe, maybe 4 billion years ago, that Earth formed or got life after, or that this catastrophe was some sort of war, or that this war was more recent and got all the intelligent life specifically, like some psychic bomb. These are very common in science fiction. Larry Niven's known space and ring world setting is an example. Mass Effect is, Stargate, Babylon 5, and tons of space opera where we try to explain why humanity might be able to emerge on a galactic stage where others are already present, but not a billion years ahead of us and occupying every planet. And viewing us as little more than primitive insects, and not because they are particularly smug or self-superior, just that far ahead, much as we are to actual insects or amoeba. The key problem here, beyond no evidence for it, which is true of nearly every Fermi Paradox solution anyway, is that our galaxy is not the whole universe, and traveling between galaxies is not that much harder than traveling across one. So you would need to assume somehow a war or catastrophe took place that got folks in something like a billion light-year wide radius, and FTL would only exacerbate that problem since a war might then be fought over such a distance, but then colonists could arrive from outside that war zone after it was done too.
See also Berserkers and Hibernating Monsters. Our galaxy isn't the whole universe. Region of galaxy.
Some regions of the galaxy may be more or less suitable for life, as we explored in our episode Galactic Habitable Zones, and while this would not fall under our rare Earth or rare Sun or solar system categories, it follows from the same principle just at a wider galactic scale. This could include local nebulae generating lots of supernovae or regions of low metallicity from not enough supernovae, or low star formation rates, proximity to large numbers of stellar remnants, being too close to the center of the galaxy, too far, and many other factors explored in the aforementioned episode, which also explores the possibility that some entire galaxies may be unfavorable to life, and that even galactic superclusters might have habitable zones.
See also Rare Earth, Rare Sun. Resource hoarding.
In the Fermi Paradox, resource hoarding covers the idea that under known physics it is advantageous to stockpile resources for future use, even if you have no immediate use for them. This is the reminder that low-hanging, easy-to-grab resources, like asteroids, are prone to getting ejected from star systems or falling into planets or suns, where gravity makes them hard to get, and that those suns themselves can be harvested by star lifting and are burning through fuel at a huge rate. Our sun goes through over 600 megatons of fusion fuel a second, energy to support untold billions for an entire extended lifetime burned every moment and wasted on lighting up the extragalactic void, with less than 1 photon in a billion destined to ever land on any planet's leaves. With that in mind, we tend to assume even civilizations that are not prone to growth and expansion are prone to wanting to harvest the galaxy, and that any major attempts to do so will automatically qualify them as loud aliens and solve the Fermi Paradox by making those efforts blatantly visible astronomically. Indeed, even a very benevolent race might build a partial Dyson swarm around a star a primitive species dwelt near, so as not to let the energy go to waste and to offer it to them as a welcome to the galaxy gift down the road. There's just too many reasons to gather those resources and too many ways it could be done, even by species who didn't want to leave their own solar system.
See also Dyson Dilemma. Rim migration.
Rim migration is the idea that cold is beneficial to post-biological life, as it is believed to make computation far more efficient with the same energy. With this in mind, it is thought that many civilizations or post-biological entities might head out to deep space both for that cold and for protection of isolation and emptiness from accident, competition, and malice. In this regard, the galactic rim and beyond seem ideal. Indeed, some thought ring galaxies might be evidence of such mass migration before we could see them better. However, there seems no clear reasons for a fast rush there by anyone, let alone everyone, so we would expect resource hoarding or even moving stars in their entirety on galactic ejection paths with Shikata thrusters or other stellar engine designs looked at in our megastructural compendium, which again might look similar to a ring galaxy while occurring.
See also Aestivation Hypothesis, Dyson Dilemma, Hermit Shoplifter Hypothesis. SETI, METI, Dysonian SETI.
SETI is the search for extraterrestrial intelligence, as well as the name of the largest group involved in that effort, the SETI Institute. While traditionally this has mostly been about turning telescopes on locations to look for signals, it also includes the hunt for techno-signatures on planets which might be visible at great distances, as well as Dysonian SETI, the hunt for Dyson swarms or Kardashev 2 or 3 civilizations. This process can include hunting for active beacons aimed at us, or overt communications we might overhear, or byproducts of such civilizations like their infrared waste heat or starship drive signatures, which might indicate certain types of power sources. You also don't necessarily need a clear signal to detect communication. Odds are good most civilizations use high amounts of signal compression even on messages which are not encrypted, and signal compression is basically designed to remove patterns from signals with a note saying the pattern was removed. A note saying the next 12,000 pixels are white is lower data than 12,000 entries in a row saying white dot here, for instance, and that makes our modern signals hard to recognize as signals and likely would make alien comms often look very noisy and harder to recognize, but you still would have large and unnatural sources of some radio wavelength that would tell you a signal was present. These are the sorts of methods SETI offers us, but we also have what is called active SETI, or METI, messaging extraterrestrial intelligences. This is where instead of pointing a telescope somewhere, we point a transmitter instead and say hello. This concerns many people as it's potentially telling a hostile civilization that you're there, but realistically, no one with practical interstellar travel who might send an armada here to attack isn't going to know we are here anyway. Earth didn't magically appear when radio was invented. It's been giving off biosignatures for most of its existence. And a civilization that can send fleets can also more easily send probes to do flybys and spot this obviously inhabited planet, at which point it would be logical to send a periodic probe or dedicate a big telescope to monitor for signs of intelligence, like tons of controlled fires, canals, roads, giant walls, pyramids, and so on, all visible from space. For this reason, METI is probably safe enough, as it's unlikely to raise our exposure to an alien menace if one is close enough to hear us. One last type of SETI of note is laser SETI, which assumes that signals are often sent by a more focused beam rather than an omnidirectional broadcast, and if someone were trying to communicate with us, they might just have a beam on our planet or our inner solar system, and we haven't spotted it yet. Although we might see scattered reflections of those beams inside highly populated alien star systems, for communication or even power transfer.
See also Kardashev Scale. Simulation argument.
Simulation argument, or simulation hypothesis, is an example of a common concept involved in the Fermi Paradox that would technically be a solution but not a very useful one. See our simulation hypothesis episode, or Are We Living in a Simulation, for a full discussion of the concept, but the usual idea is that if it is possible and practical to emulate or simulate a human mind, then it is very likely any universe it is possible and practical to do this in likely has many simulated realities built inside it, and thus it would be more likely than not that if such sims are possible and practical that you are in one, as they make up the majority of realities with intelligence in them. This mostly does not impact the Fermi Paradox in the sense that everything we see is simulated and odds are good whoever built it kept the internal physics similar to their own and self-consistent. So if they only want one civilization per supercluster, they just tweak the initial conditions to match that. If it is an ancestor simulation specifically, then it is assumed to be identical to ours in nearly every respect, and likely has the same reason for the Fermi Paradox. However, there are a lot of caveats and cases where this universe being a particular type of simulation, or certain apparent conditions of the universe, might be telltales of simulation, such as a nursery universe or zoo hypothesis and quarantine hypothesis. See those episodes or entries for more discussion.
See also Boltzmann Brain, Quarantine Hypothesis, Zoo Hypothesis. Solution exacerbates the Fermi Paradox.
Many solutions to the Fermi Paradox proposed to explain why aliens might be common but unseen tend to rely on a technology or ability that, if true, would in some way make the universe we see even more paradoxical. For instance, faster-than-light travel not only makes colonization of your neighboring stars easier, but it means aliens who originated in our galaxy 10 billion light-years from here just a million years ago might have been able to reach Earth by now. Alien phenomena being explained this way is also common, and suggesting a UFO might not be a spaceship but a time traveler or from another dimension just opens the door to wondering why we're not seeing more of those, getting visitors from the year 1 million AD, and so on, which tend to require suggesting things like prime directives of non-interference or not messing with time. Generally speaking though, any suggested solution to the Fermi Paradox which makes space travel easier or widens the range of that travel in space or time, or multiverses, only exacerbates the fundamental problem that the universe is old and ancient and seemingly full of planets that might have produced intelligent life before our planet even formed. Throw in worrying about planets that won't form life for another billion years but could travel back in time to now and colonize the universe, or some Boltzmann brain from some reality unlike ours, or us being in some simulation, and things only seem more implausible. But even relatively mundane technologies like a sci-fi force field or cloaking field on some UFO tend to imply technologies that make space colonization much easier. So I tend to discourage folks from casually suggesting these without considering the additional abilities and ramifications of such technology.
See also Boltzmann Brain, FTL faster than light travel, prime directive, simulation argument. Stellar neighborhood.
The region of the galaxy you are in and the conditions of your own sun and solar system are likely to be factors in the Fermi Paradox, but your local stellar neighborhood is likely to be a significant filter. Binary systems are likely to have problems with life, but mini-stars, while not binary, may have neighbors just light months away, not light years, with other stars being mere light days from the system center. Dense and younger star collections are likely to be subject to mini-giant supernovae, followed by a second wave of white dwarf supernovae in binary systems. Other stars may be in nearly deserted neighborhoods, arising from pockets of space with low metallicity and thus having few rocky planets. Indeed, a great many stars are between galaxies and may lack planets or have few of them, and be very far from any plausible colonization option, making colonial scenarios like Percolation Theory more likely to apply. These and many other factors may make certain stellar neighborhoods harsh for life.
See also Filter, Percolation Theory, Rare Sun, Region of Galaxy. Techno and Bio-Signatures.
Techno-signatures and bio-signatures are terms for telltale or overt signs of the presence of technology or biology. This is a ballpark term, but we often are referring to astronomically visible examples, such as a spectrum of light off a planet indicating a high concentration of free oxygen, which we assume is rare outside of active biology, releasing oxygen as a byproduct of photosynthesis. So too, carbon dioxide in higher quantities might indicate a large industrial presence, or the night side of a planet might give off more light in the visible spectrum than we might be able to explain by natural causes. One of our key concepts for attempting to distinguish between strange natural phenomena and artificial constructs or alien civilizations is our assumption that often the presence of one possible bio or techno-signature will be accompanied by other ones. On closer scrutiny, one is likely to be most easily visible, potentially by orders of magnitude, but by examining the origin of that signature, we should expect to see some additional ones, and now that we have discovered tens of thousands of exoplanets, with more being found every day, it may be we will soon start seeing possible signatures of life.
See also Loud Aliens. Technological Singularity.
Technological singularity is a broad concept we've discussed in multiple dedicated episodes, but in the context of the Fermi Paradox, it is usually the assumption that some AI or post-biological life will almost inevitably emerge in the same period as a civilization is first exploring space, thus could wipe out virtually all alien intelligent races before they colonize the galaxy, and us too. As such, it is treated as a late filter to the Fermi Paradox. However, it only operates that way in contexts where that hyper-advanced mind either rapidly shuts down after killing everyone off, never desires to leave its homeworld, or figures out how to migrate to a better universe or reality. As such, most of these variations would seem to just replace Homo sapiens with AI or transhumans, much as we are thought to have replaced earlier iterations of humanity, either substituting ourselves or mixing with them. In any event, the Fermi Paradox would be unaffected by this option specifically, as it simply falls under one of our other solutions dealing with high intelligence not being inclined to galactic colonization or imploding somehow.
See also Ascension, Boltzmann Brain, Dark Forest Theory, Inevitable Intelligence Implosions, Late Filter, Miniaturization, Nihilism or Ennui, Rim Migration. Technological Time Bombs.
Technological time bombs, also sometimes called honeypot technologies, are a type of late filter, discussed in more detail in our Technological Time Bombs episode, but cover those technologies which are so attractive to use and inevitable to discover that we can assume virtually every civilization figures them out and tries them, which contain some sort of risk. Common examples suggested are fossil fuels, atomic energy or weapons, computers and AI, entire fields like particle physics or psychology and neurology, and anything which might be viewed as dangerous to continued survival, which I've even seen include medicine on the grounds it allows overpopulation, or birth control on the ground it causes population drop-off, though usually what we mean is something that seems safe and that once you begin using it is either so addictive you ignore the dangers or which never shows any signs of it till the last minute. See that episode for more examples, but as filters go, this could range from something that about half of civilizations discover and kill themselves on, to some technology so insidious and safe-seeming that merely using it one time guarantees obliteration, and thus would be a great filter of the Fermi Paradox. Late filter proponents tend to assume that it is not that a single technological time bomb gets us, but that several, each with decent odds of taking us out, contribute to a stronger filter, and we refer to this as a technological minefield.
See also Great Filter, Inevitable Intelligence Implosions, Late Filter, Technological Singularity. Tectonic activity needed.
Earth has a great deal of tectonic activity, and we do not know how common that is and what causes it, though we assume our size and the presence of our moon are big factors. Without it, not only might a planet get saturated in free oxygen very quickly after life forms, but many critical geological and hydrological cycles might fail to function. This could result in far more desert planets or planets entirely covered in oceans than we would expect, especially given that a mountain sticking up through an ocean experiences a lot of erosive force from sea and sky. This activity can potentially thaw a planet out that is turned into a snowball Earth, which we expect is a common event, and indeed may have happened to Earth repeatedly, by covering the surface in dark and sun-absorptive ash, and provides the critical deep-sea thermal vents that are the current favored candidate for abiogenesis and the origin of life on this planet. It also opens the door to life emerging inside large, tidally racked icy moons of gas giants, such as Europa. This may also represent a time limit on longer-lived stars, as the tectonic activity of a planet should decrease over time and may leave a short window in which life arising on it is probable. Alternatively, too much tectonic activity might render a planet uninhabitable, or prevent anyone ever forming cities and civilization. For this reason, it is considered a strong filter candidate of the rare Earth variety.
See also Filter, Large Moon Needed, Rare Earth. They are talking, but we can't hear them.
This is the general category for Fermi Paradox solutions that assume they are actively talking and we just can't make it out. Reasons include that they are too far away, that the signal gets lost in the noise, that they don't use light to communicate, or that we can't log into their network, both of which have their own entries. But the idea that signals can be lost in the noise, while valid in the sense of trying to find a duplicate Earth or listen to their interplanetary chatter, tends to get overextended. I often hear folks say no radio signal could be heard more than 100 light years away or maybe 1,000, and what this actually means is that we, using our present tech, would have a problem hearing the routine radio traffic of our own current planet, or a duplicate, more than that distance away. The notion that radio signals or laser comm beams built by advanced civilizations for the explicit purpose of talking to civilizations like ours and could not be heard far away is absurd. As far off as we can see the light of a star or do radio astronomy, someone could communicate to us. It simply requires more power and lower amplitude, and for an intuitively simple if over-the-top case, some civilization could build a big solar shade or mirror near their sun and flicker it on and off to significantly alter that star's brightness in a repeating pattern of binary digits of pi or perfect squares, and that would be visible galaxies away and could be accomplished by nothing more complex than a very dumb clanking self-replicator and not one drop of new science. It would also not be very hard to send focused beams or lasers with greetings to any planet you could see biosignatures on astronomically. For this reason, the idea that distance is a solution to the Fermi Paradox only holds if we are talking about civilizations that are talking but not interested in talking to us, and this bumps heavily into non-exclusivity in any setup where interstellar travel and colonization is viable, or Kardashev Scale civilizations are.
See also they don't use light to communicate. They don't want to talk to us. We haven't logged into the network yet. They don't use light to communicate.
SETI, the search for extraterrestrial intelligence, has tended to focus on listening for radio waves or other electromagnetic radiation that might contain alien communication signals, and a common concern raised with this is that aliens might have some better method of communicating, such as a faster-than-light technique using some advanced technology we are not privy to. Or even the communication might be point-to-point laser beams that are so highly compressed they look like noise. This, in and of itself, would seem like a decent explanation why we don't hear their normal communications, But to be a good Fermi Paradox solution, it generally requires an assumption that any alien race simply assumes you will figure this technology out fairly quickly, especially in galactic timelines, so that shouting across the galaxy in radio is seen as a waste of time. As a civilization might spend many millennia in Stone or Iron Ages, learn radio for a century or two, then come across hyperwave transmitters and be able to instantly talk to everybody. Those extra couple centuries might not seem like they're worth much effort, especially since it's a period where a civilization is likely to have gotten much better at recording its own history, so little understanding of them is likely to be lost by this delay. All of their new events, art, and learning are going to be digitally recorded and backed up. However, this has three major problems. First, it does require that there is some significantly better form of communication available than radio, and that is at odds with known physics. This isn't a compelling problem for many who assume FTL exists, of course. Second, it assumes civilizations wanting to make contact are not worried about civilizations going extinct where they have radio, and probably also have weapons of mass destruction and computers that might spawn AI. This one doesn't bug me because I have never found the idea that we blow ourselves up and go extinct very likely, and if AI is very likely to replace biologicals, then odds are good aliens out in the galaxy don't consider that a big deal and may often be alien AI themselves. The third reason, though, is more compelling, as it's assuming a civilization wouldn't just keep a beacon running in normal radio pointed at planets that had complex life. A beam transmission in whatever frequency could be maintained on a star about as wide as its habitable zone for a rather trivial cost in energy given the scope of even fairly modest advanced civilizations, and that signal might simply contain a hello message, Rosetta Stone, and blueprints for a communication device. Same if you have FTL communication, it only exacerbates the issue of why you're not sending out colony ships or at least regular flyby probes or monitors of any interesting system. Any single Kardashev 2 civilization should find it trivial to maintain such coverage even if they were sending a 10-ton probe to 100 billion different candidate star systems and a new one every millennia.
See also FTL faster than light travel, Kardashev Scale, Non-Exclusivity. They are talking, but we can't hear them. SETI. We haven't logged into the network yet. They don't want to talk to us.
The idea that aliens don't want to talk to us generally relies on one of two lines of reasoning. One is that they have some rule against it, such as the Star Trek Prime Directive, which has its own entry, and the other is they don't find us too useful or appealing. Maybe they find us mundane and boring, maybe they actively loathe all aliens, but talking to us doesn't seem useful. This has a lot of problems, the first being non-exclusivity. Some aliens are bound to want to chat with us, and if Earth is boring, well, I've heard my own home state of Ohio called that a lot, and Kansas is almost legendary for being a boring backwater, and yet both enjoy large tourism trades. They may think of us as little more than animals or be giants in the playground, with us mere insects to be stepped on, and yet plenty of people find animals and insects interesting, and certainly would talk to them if they could usefully reply. So this one always strikes me as implausible, because if life is so common our pale blue dot is boring, then it would also imply life was so common there would be tons of worlds nearby who had a small minority of academics or amateurs with weird or eclectic tastes who found us interesting.
See also Earth and humans are boring, Non-Exclusivity, Prime Directive. They hide from everyone.
The idea that secrecy can keep a planet safe from hostile invaders is a popular one, and key to many Fermi Paradox solutions, but as we explored in our episode Hidden Aliens, our current understanding of physics and our own history push back strongly on this as a useful strategy. Hiding your planet and not expanding to other worlds is most likely to result in someone expanding and coming across it anyway eventually, and that invader now has the resources of 1 million solar systems behind them to handle any conflict. Stealth is very hard in space, and while technologies might exist to hide them from us, they should most desire to hide from a more advanced civilization that could be a real threat, who is likely to have this same technology and know how to defeat it. Any given stealth technology would rely on ensuring no one in your species could wreck it with a broadcast or accident, and still only protects you from anyone not yet existing when you develop this technology. After all, if your civilization wants to hide from an older, bigger, and more advanced civilization, they would need to have hidden backwards in time before they sent out their first loud radio signals, as that other civilization has probably long since detected their planet's primitive biosignatures and sent probes or turned telescopes on it. Nonetheless, there may be certain technologies, like shunting your planet into a pocket universe or empty section of a multiverse, which would hide you in a way that could not be followed or which no one would be motivated to search for.
See also time travel. They hide from us. They hide from us.
While the rule that there is no stealth in space seems to make hiding your civilization rather futile, especially from older and bigger civilizations that would have seen you before you tried hiding, there is the possibility that you simply try to hide from humanity, either us specifically or under some general prime directive of not wanting to interfere in other civilizations. This does not function under the Dyson Dilemma, which would leave alien civilizations blatantly visible to our modern civilization now, even if they had left the globe of a few hundred light years of free stars around us as a gift for our eventual entrance into the galaxy. Such a gift of nearly 1 million stars is still plausible in a galaxy of nearly 1 trillion of them, but less so if you're trying to hide Kardashev 3 civilizations from any species which is up to 20th century technology. And the Fermi Paradox is about our inability to see these folks, not our ancestors. The issue here is that it is hard to imagine any civilization deciding that giving us another century of isolation was worth leaving an entire region of the universe empty, instead of a tiny corner of one galaxy. But of course this assumes what we are looking at is genuine. One of our probes might bump into a big TV screen one day, or maybe everything that leaves cislunar space gets quietly grabbed by aliens and its feed hijacked for simulation. Or the aliens in the real universe we're from might be so grand that tossing us in our own private universe was considered no more effort or generosity than dumping a petri dish bacterial culture in its own private pond. Scale is always relative, and they may have universes in abundance to give away. Or we may not even have a world and live inside a virtual reality laboratory experiment. See our episode The Galactic Laboratory for more discussion of that.
See also Kardashev Scale, Simulation Argument, Quarantine Hypothesis, Zoo Hypothesis. They hide here on Earth.
Aliens among us is a common belief and one many feel there is strong evidence for, and while I do not share their opinion, it is still possible to contemplate that scenario and ask what might be implied about their goals, motives, or behaviors based on those traits apparently exhibited in our current understanding of the universe. Indeed, this is the primary avenue used for discussion in our Alien Civilization series, and explored in detail in our Secret Aliens and Covert Aliens episodes. What is usually implied is that the aliens have some reason for being here: anthropology, collecting primitive relics, or tinkering with society to make an easier transition into their empire. Any of these may be true, but require us to first and foremost ask on any given theory if there is an easier way to achieve their goal, and to assume they have an overwhelming advantage in technology and arms to us, though not necessarily to other actors on the local galactic stage who may object to their behavior. Many scenarios play out different with multiple players, not just them versus us. For instance, an anthropologist has an obvious motive for living covertly with us, but could remote control an android or be implanted into one, or send tiny drones concealed as birds or even insects to watch us, all from orbit, and should have no need to do this at this point, as our core makeup should be no different than a few centuries ago, or longer, and simply watching TV and keeping a link into our internet should allow good monitoring. Aliens might abduct us for medical reasons, but should have been able to abduct a library more easily, and could get a ton of our DNA off those books or letters or coins in a vending machine. There should not be many reasons why their research requires a live human. And given that they want to be secret and apparently get caught at enough for many folks to believe they do abductions, they should be reserving that approach for the minimum times it's needed in favor of sneaking bodies out of graves or sneaking a brain scanner or compact alien MRI into someone's bedroom. Ultimately, this area can never be ruled out, as there are clearly motivations to come to Earth and hide from us, but many lack consistency or grow needlessly complex. So it is important to not only apply Occam's razor, but to simply ask if you can think of a less convoluted way to achieve the apparent alien goal, or one with less chance of exposure, because they are intelligent and so they probably could too.
See also cosmic collectors, they hide from us. Tidal locking.
Our moon, like most moons, has slowly had its rotational energy bled off, so that it keeps the same side pointed at its planet, and we believe the same thing can happen to stars and is more likely the closer you are. As a result, planets around dimmer stars, which is the supermajority of them, need to be closer to their sun for them to be in the habitable zone, and thus may be tidally locked, showing one side to that star for an eternal day and the other in perpetual darkness. There is a good deal of uncertainty how often this occurs and around what stars, and if such planets might be hospitable to life, something we explored more in Colonizing Red Dwarfs. For further explanation of how tidal locking occurs, see our episode on tidal locking. Note that in general, tidal forces are likely to be very important to the habitability of any planet or moon.
See also filter, Goldilocks Zone, rare Earth, rare Sun. Time elapse argument.
Astronomy is history. The further away we look, the further back in time we look, and this gives us a useful tactic for examining strange astronomical phenomena and asking if they are natural or not. This is where the time elapse argument of the Fermi Paradox, or T, comes in, that any phenomena suspected of being an artificial construct should grow rarer the further away or back in time we look. If it is not, then it is probably natural, and quasars are an example of that. We wondered if they might be alien signals originally. Indeed, realizing they were brighter objects than not just stars but entire galaxies did not make us think they had to be natural either. We just wondered if they might be mega-Dysons, Kardashev 3 civilizations. But as we mapped them out and checked the distance over the decades, we found it was very rare to find any within a couple billion light years, and that they were most common about 10 billion light years away, or 10 billion years ago. And yet it would seem very implausible that enormous K3 civilizations were popping up all over the universe when it was younger than Earth was when the first brain evolved here. Same, it would be implausible that these became rarer over time, and if you're thinking maybe some civilizations evolved faster than us, that would work, but we have quasars detected that are fully 13 billion years old, probably older than any rocky planet. We can use this in other cases, like ring galaxies that people thought might indicate a wave of Shikata thrusters pushing out to indicate a civilization engaging in rim migration, but it falls apart under the lens of T. Any artificial phenomena should appear more common as we move forward in time and more civilizations develop and grow. If it isn't, it probably isn't a sign of an artificial phenomena, and if it is the reverse, shrinking with time, it is even more likely it is natural.
See also rim migration, time travel. Time travel.
Time travel matters to the Fermi Paradox in two major ways. First off, virtually any form of faster-than-light travel tends to imply or even require a time travel function if it does, raising paradox issues with galactic civilizations having FTL. And second, that much like FTL or multiverse travel, time travel only exacerbates the Fermi Paradox. If it works, we have to worry not just about older civilizations visiting us, but our own descendants. As we looked at in our episode Time Wars, you would expect to see people invading from the end of the universe back to the beginning of time. Somewhat amusingly, as we saw in that episode, the sheer number of people en masse moving from a billion timelines back to some earlier root period could cause a localized black hole or even Big Bang in certain conditions and models.
See also FTL faster than light travel, interuniverse migration, multiverse and alternate reality aliens. Solution exacerbates the Fermi Paradox. Type of star.
While falling under the general heading of the rare sun great filter, the type of star a planet is around deserves special note as it represents such a large category of uncertainty. On the one hand, stars shorter lived than our own sun would not seem great candidates for the Fermi Paradox, especially as stars grow brighter with time, moving habitable zones, and shorter-lived stars do this faster. Alternatively, longer-lived stars would seem to offer stable habitable zones for extended periods. But many may cause tidal locking to their habitable planets, rendering one side eternally lit and the other dark, though this is now disputed too. Stars with too much solar variability might roast planets periodically while freezing them in between, or strip off atmospheres with regular and powerful solar flares and coronal mass ejections. And this doesn't even contemplate strange stars like binaries, supergiants, brown dwarfs, stellar remnants, variable stars, and more, none of which should be ruled out for the presence of life. Indeed, all of which are also plausible for colonization by technological species, not our more classical notion that only rare Earth analogs around yellow suns would be good homes for humanity, an assumption which is critical to solutions such as the Aurora Effect or Percolation Theory.
See also Aurora Effect, Percolation Theory, Rare Sun. Universe too young.
The idea that the universe is too young yet for life to exist is generally predicated on the notion that it takes many cycles of star birth and death for heavier elements critical to life and rocky planets to reach much abundance and distribution. So too, the current form of galaxies, for instance, is mostly larger ones like ours, composed of many smaller galaxies that have been forming and being swallowed, and as such we will soon merge with Andromeda and a few others to form a single big galaxy, surrounded by the emptiness of Hubble expansion. Most other galaxies are in the same process, which can cause vast sterilization events and planetary ejections. For the next 10 to 20 trillion years, 1,000 times the age of our universe, stars will be common, and only for another several billion will there be much chaos of galactic mergers. So the universe is likely to be far more hospitable to life emerging then, and many have been far harsher on life before then. The issue here is that so long as loud aliens is the norm, especially Grabby Aliens, we would expect that galaxies would be claimed not by the thousands of intelligent species that might arise in a more hospitable later universe, but rather by the first one that managed to avoid dying in that harsher earlier universe with fewer rocky planets and more vicious galactic conditions and lived long enough to build a ship. We might be such an example.
See also Grabby Aliens, Loud Aliens. Virtual Reality Utopia.
A common counter-argument to us colonizing space is that we might instead colonize virtual worlds, places likely to be far stranger or more paradise-like than habitats we might build or worlds we might find and terraform, and made quicker too. This is not a good Fermi Paradox solution though, because even ignoring that many people would probably skip on this path under non-exclusivity, then AI would still let you do things in reality by advanced automation. Any level of AI able to produce virtual realities the overwhelming majority of people would find better than reality is also sufficient to program von Neumann probes to go out and colonize the galaxy or grab resources to bring home to build more and grander computers for simulating reality for more people and greater quality. In the end, it's no harder to program a robot to make copies of itself and grab rocks than it is to program a convincing NPC for a game, and probably easier. So before you reach an addictive level of virtual utopia everyone would go into, you should have been able to send out the drones to grab a vast supply of material and fuel.
See also Non-Exclusivity, Resource Hoarding. Vulnerable World Hypothesis.
Some technologies allow a small group or individual to be extremely lethal, and there is a concern that in the future it would be impossible for us to limit access to destructive weapons. As an example, a Star Trek replicator might be used to make doomsday devices, or a 3D printer, and even if only 1 in a million people would do that, several thousand such lunatics could wreck civilization by each setting off a multi-megaton nuke or unleashing grey goo. Indeed, the fear of options like this might drive the sort of migration we contemplated in our hermit shoplifter hypothesis, where everyone runs for the proverbial hills of intergalactic space as small groups or individuals, simply because they consider it impossible to safely live in any civilization of size for any real length of time before it would implode or turn into a police state. We do not know what sort of technologies are on the horizon though, both for making such doomsday devices and protecting against them. And a point I often like to make on the point of crazed madmen in the future is that we don't just have the physical sciences to advance, we also have medicine and psychology, which might make detecting lunatics early and treating them so easy and effective that this sort of scenario is not a concern. This varies slightly from technological time bombs, nihilism or ennui, or inevitable intelligence implosions, in that the assumption is the civilization is healthy enough overall and the technology is inevitably destructive, just that the bad eggs exist in such civilizations it might only take one bad egg in a billion to lay everyone low.
See also Hermit Shoplifter Hypothesis, Nihilism or Ennui, Inevitable Intelligence Implosions, Technological Time Bombs. We are aliens.
One notion for explaining why aliens aren't constantly invading us is that they already did, and humanity is some abandoned colony or second evolution of their species. This one is incredibly popular in science fiction, as it gives us an excuse why all the aliens look like somebody glued a piece of rubber to a human head or painted them, with the other being that the humanoid form is so handy that evolution converges toward it a lot, in spite of it not even doing so on Earth. Not many bipeds have separately evolved here, and the conditions are the same, which they would not be on some alien planet. We could suppose aliens came here thousands of years ago and inspired all mythologies, also a popular sci-fi topic, but it is hard to match all fossil records to the idea of aliens coming in and breeding with us, which, beyond being a rather bizarre and disturbing thing to do, also has a lot of technical issues, albeit, as we've discussed in other episodes, with enough technology you can crossbreed anything, half man, half turtle, walking human tree, or weird alien love child with cool elf ears like Spock, or maybe tentacles. This also need not necessarily be literal but more psychological, in opposition to the idea that aliens are alien, and instead that aliens have a lot of the same motivations and behaviors we do. But when it is more literal, you begin to need a fair number of hand waves to make it work, the biggest of which is what has happened to them since then. Hand waves isn't necessarily wrong though. In a scenario like the Aurora Effect, where colonies are rare and not very successful, and interstellar travel is never very quick or practical, you could easily have colonies that fell to techno-primitivism and lost their history. But to account for a fossil record like ours, you either need to back it up to the beginning of life, an alien scout landed here 3 billion years ago, and their suit leaked microbes onto the planet, for instance, or you need to find a plausible injection point, like arguing that we are assuming a gap in that fossil record has a missing link but it does not. That's when alien life showed up. Our fossil record gets better every day, but it's still very spotty, and as we discussed in the Solarian hypothesis, technological remains of a colony might be utterly gone after 1 million years or so. One other option is that the aliens in question are very casual about bioforming, so they just slide right into the existing ecosystem, and maybe even hijack existing bodies of, in our case, some clever primate with useful hands. Those are big stretches, but may be possible, especially if space travel is really difficult and civilizations rarely last long. See this weekend's upcoming episode, Human Aliens, for a deeper dive on this topic, both if we might be aliens and convergent shape evolution.
See also Aliens Used to Visit Earth, Ancient Aliens, Aurora Effect. We haven't logged into the network yet.
A subcategory of the concepts that aliens might not use light or radio to communicate, or that they are talking but we can't hear them, is that there's a galaxy-wide network or internet equivalent, or even universe or multiverse-wide one, and that we don't have the technology or passcode for it. In a non-FTL context, this could also be a decryption key or compression algorithm for mundane radio traffic, though the internet is usually a FTL method. This has the same problem other solutions of this category have, of non-exclusivity, in that unless Kardashev Scale civilizations are very rare, there is no reason to expect every civilization feels it is wasteful to run a beacon with a hello and construction diagram to primitive planets. However, this does leave some options for communication only being possible by some exotic method in cases where someone might be transmitting from some other reality or dimension.
See also Faster Than Light Travel, Kardashev Scale, Non-Exclusivity. They are talking, but we can't hear them. They don't use light to communicate. SETI. Zoo Hypothesis.
Zoo Hypothesis is an appropriate last entry, as it is an example of a Fermi Paradox solution that cannot be disproven and has a large number of motivations and reasons why you might do it. This is the basic notion that the universe as we see it around us is either concealed or false. It might be that you're in a simulation or that your world is englobed in a very large television, and every deep space probe we sent out got grabbed and hijacked to send false signals back, or even that we've been subtly drugged or tricked to ignore them, or the universe with them is easily visible, but they've adulterated our science and evidence so that everybody just assumes the universe is empty because all our telescopes and astronomers are really alien-possessed. There is an endless list of options, but more importantly, many plausible motives for doing it. Everything from a lab experiment to an amusement or a way to raise and protect civilizations. See our episode The Fermi Paradox Zoo Hypothesis for details.
See also Quarantine Hypothesis, Simulation Argument.
And that will wrap up our entries. Given how long this episode already is, I'll keep our endnotes fairly short, but for those curious, I decided to redo this episode last year, but I knew it was going to be a behemoth to write and produce, roughly parallel to an entire month of work, while still being just one of 8 episodes this month, including our Nebula exclusive, ultra-relativistic spaceships. I also wanted to wait till after the surgery and speech therapy I had earlier this year had gotten rid of my speech impediment, and while I gather it's very diminished, I think it's still present, and given that this outro segment was recorded later than the rest of the episode, it might be more noticeable here. In any event, as always we will run our credits right after the schedule of upcoming episodes, but I wanted to take a moment to thank all the folks over the years who discussed the Fermi Paradox with me, even before this show, and helped me brainstorm or polish, challenge, and critique our discussions of the topic. That's at least many hundreds of people, including a lot of our audience, and for all of you who have, thank you, and I hope you'll continue doing so in our YouTube comments or on our social media platforms. And for everyone who has made it through over 3 hours of me discussing this, thank you for tuning in this week. We're still not done for the week though, as we have our Sci-Fi Sunday episode on human-alien hybrids, or the idea that we might have originated from another planet, coming up this weekend, followed by a look at how we can build domes on Mars, and if we should compared to underground habitats, and we will see the construction options and weigh the pros and cons next Thursday, November 16, 2023. Then we'll examine the astronomy of double planets, where the big object in the sky isn't a moon, but a much larger and bluer and greener planet, and ask if life might be able to arise on such worlds and migrate between them. Then our monthly livestream Q&A is cancelled this month, and indeed next month will be our last livestream for the foreseeable future, but we will still be having a short episode that day on space hygiene, our most recent winning poll topic, before closing the month out on November 30th with Agri-Worlds, and a discussion of how you could farm an entire planet. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, along with hours of bonus content at go.nebula.tv/IsaacArthur. As always, thanks for watching, and have a great week.